So the first topic of this course is Introduction to Networking. And we're going to start from the beginning, gently assuming that you don't know anything. Now, here's the content of the Introduction to Networks. First, we'll have a brief look at what's a network. Then, we'll talk about physical network topologies. So if you look up in a dictionary, you'll see the concept of networks as people or groups communicating with each other. Similarly, in the IT sector, the concept of the network appears as the whole formed by the connection established between computers, usually using a cable to communicate with each other and transfer data to each other. Local area networks are computer networks that connect devices in limited and close areas, such as workplaces, residences, offices, schools, campuses, that sort of thing. So in this way, computers, printers, various network devices can communicate with each other. So in the figure here, you can see that 3 computers are connected with the help of switches, and they exchange data. Even though you might not know what a network device called a switch is yet, don't worry, we will learn each network device in detail. For now, just know what the local area network does. Wide area networks are private communication networks that cover a wider geographical area, such as cities, countries, and include multiple local area networks. Now, as you can probably guess, the largest wide area network available is on the Internet. So in a wide area network, router devices are used to connect more than one local area network. With the help of routers, it's possible to connect all networks belonging to this wide area network with each other. You may be new to the names of network devices and may not know exactly what they do, but you will learn, and you will learn each of them. So we won't pursue the details at this moment, and we're going to talk about the differences of wide area networks from local area networks. So in the following sections, we will cover the wide area network in much more detail. Now, there are many devices between LAN and WAN, but the most well-known are the ones seen in the figure. While LAN is used in areas such as homes, schools, and offices, WAN can cover cities, countries, or even the whole world. It uses technologies such as Ethernet and Wi-Fi. LANs have higher transfer rates than WANs. LANs are both less costly and have lower maintenance costs than WANs. LANs can be created with simple network devices such as switches and hubs. WANs need devices such as routers and gateways. It's much easier to understand the problems in the network in LANs than in WANs. CAN. So it stands for Campus Area Network. A CAN is a network that spans an educational or corporate campus. University campuses and company buildings are some examples. So a campus area network is larger than a LAN as it can span multiple buildings in a given area. It usually consists of several LANs. They work similarly to LANs in that users with wired or wireless access to the network can communicate directly with other systems on the network. SAN, or SAN. Now, with the increase in Internet usage all over the world, data usage and sharing have also increased. So for this reason, existing data storage solutions, both personally and institutionally, just weren't enough. Every year, we produce and share much more than in previous years. So it looks like it's going to continue like that for a long time. Data storage will always remain a necessity in our lives. SAN, or Storage Area Network Technology, was developed with the inadequacy of existing technologies in mind. So this term, which is used as storage area network in our language, is a type of network that provides a fast and secure connection between servers and storage units. For example, let's consider a standard LAN network. All users in this network use the network for all kinds of purposes. Since file servers are located on the same network as a general network traffic, it causes a decrease in efficiency. So when this connection is moved to a completely different network, it's not affected by daily usage, allowing us to get higher performance results. OSI reference model. So up until now, we've been introducing you to the concept of a network, but that's the first chapter. Now, since we're beginning the second chapter, we want to talk about the OSI reference. So here's the content of the OSI reference model. First, we'll have a brief look at the internetworking models. Then we'll talk about the OSI reference model. And then finally, we'll cover the subject of encapsulation. So way back in early networks, computers could only communicate with computers of the same manufacturer. To eliminate this problem, the International Organization for Standardization developed the OSI model. Now, the purpose here is to define how the communication between the two computers will be. So this standard, which was first revealed in 1978, was published as an OSI, Open System Interconnect, reference model in 1984, with the help of new regulation. In the pre-OSI era, there were networks specific to organizations that produce computer hardware only. The properties of these networks were often defined to allow only that manufacturer's hardware to be connected. The OSI model does not differ according to any type of hardware or computer network. In fact, the purpose of OSI is to enable network architectures and protocols to be used as a component of a network product. Now, the OSI model is divided into 7 layers. So in short, a reference model is a conceptual blueprint for how communication should take place. It takes all the processes necessary for effective communication and divides these processes into logical groups called layers. Each layer has different tasks and communicates with the same layer on the device it's communicating with. When a communication system is designed in this way, it's known as a layered architecture. So let's say you start a company. When establishing this company, you will assign different people to each department. For example, we'll assume that there are departments such as human resources, advertising, and accounting. So the people you assign in human resources don't actually interfere with the affairs of the accounting department, and those in the advertising department do not interfere with the work of human resources, right? So each department is responsible for its own work. So within this scenario, I'm using departments as an example for layers in a communication system. For things to run smoothly and correctly, the staff of each department must do their job. They must rely on others to competently carry out their own unique responsibilities. So OSI is a reference model for how applications can communicate over a network. A reference model is a conceptual framework for understanding relationships. The purpose of the OSI reference model is to guide vendors and developers so that digital communication products and software programs that they create will interoperate, and to facilitate clear comparisons among communication tools. So most vendors involved in telecommunications attempt to describe their products and services with the help of the OSI model. And although useful for guiding discussion and evaluation, OSI is rarely actually implemented, as few network products or standard tools keep all related functions together in well-defined layers as related to the model. Developed by representatives of major computer and telecommunication companies beginning in 1983, OSI was originally intended to be a detailed specification of actual interfaces. But instead, the community decided to establish a common reference model for which others could then develop detailed interfaces, which in turn could become standards. OSI was officially adopted as an international standard by the International Organization of Standards, which we refer to as ISO. So not to be confused, the main concept of OSI is that the process of communication between two endpoints in a telecommunication network can be divided into 7 distinct groups of related functions or layers. So each communicating user or program is at a computer that can provide those 7 layers of function. So in a given message between users, there will be a flow of data down through the layers in the source computer, across the network, and then up through the layers in the receiving computer. The 7 layers of function are provided by a combination of applications, operating systems, network card device drivers, and networking hardware that enable a system to put a signal on a network cable or out over Wi-Fi or some other wireless protocol. The 7 open systems interconnection layers are the application layer. This is the layer at which communication partners are identified. Is there someone to talk to? Network capacity is assessed. Will the network let me talk to them right now? And that creates a thing to send or opens the thing received. Now, I want you to please note that this layer is not the application itself. It's a set of services an application should be able to make use of directly, although some applications may perform application layer functions. The presentation layer. This layer is usually part of an operating system, or OS, and converts incoming and outgoing data from one presentation format to another. For example, from clear text to encrypted text at one end and back to clear text at the other. The session layer. This layer sets up, coordinates, and terminates conversations. Services include authentication and reconnection after an interruption. On the Internet, Transmission Control Protocol, or TCP, and User Datagram Protocol, UDP, provide these services for most applications. The transport layer. This layer manages packetization of data, then the delivery of the packets, including checking for errors in the data once it arrives. On the Internet, TCP and UDP provide these services for most applications as well. The network layer. So this layer handles the addressing and routing of the data, sending it in the right direction to the right destination on outgoing transmissions and receiving incoming transmissions at the packet level. IP is the network layer for the Internet. The data link layer. This layer sets up links across the physical network, putting packets into network frames. This layer has 2 sublayers, the logical link control layer and the media access control layer. Ethernet is the main data link layer in use. The physical layer. This layer conveys the bit stream through the network at the electrical, optical, or radio level. It provides the hardware means of sending and receiving data on a carrier network. Now, when a computer transmits data to another device over the network, the data goes through encapsulation. That is, it's wrapped in protocol information at each layer of the OSI model. New information is added at each layer, and each layer uses protocol data units, or PDUs, to communicate and exchange information. PDUs are called segment at the transport layer, packet at the network layer, and frame at the data link layer. Finally, the data is converted into bits in the form of zeros and ones to be transmitted in the physical medium. Layers communicate only with the same layer on the receiving device. You should know the sublayers of the data link layer. In addition to the OSI layers, the only layer that has sublayers is the data link layer. And it's extremely important to know the functions of these sublayers. The data link layer has 2 sublayers, LLC and MAC, Media Access Control. So the LLC sublayer is primarily responsible for multiplexing network layer protocols. The MAC sublayer is responsible for physical addressing and determining the appropriate time to place data on the network. So Ethernet has been a relatively inexpensive, reasonably fast, and very popular LAN technology for, several decades. It was commercially introduced in 1980 and first standardized in 1983 as IEEE 802.3. It has since been refined to support higher bit rates and longer link distances. Ethernet has since become the most popular and probably the most widely deployed network technology in the world. Many of the issues involved with Ethernet are common to many network technologies, and understanding how Ethernet addresses these issues can build a foundation that will improve your understanding of networking in general. So let's keep the design principles of Ethernet simple. The basic idea of its design is that multiple computers have access to it and can send data at any time. If two computers send data at the same time, a collision will occur. And when this happens, the data sent is not going to be usable. In general, both computers will stop sending and wait a random amount of time before they'll try again. Now, a special protocol was developed to deal with such problems. It's called Carrier Sense Multiple Access with Collision Detection, or it might be easier to say CSMA-CD. Today, Ethernet cables look like, well, thick telephone cables. Modern cables connect to hubs or switches, and each cable runs from a computer's network interface card, the NIC, to such a box. Now, here are the most widely known Ethernet cables. 10-base-2 and 10-base-5 cables are what I would call retro coaxial cables. You don't see them much today. Each computer has a T plugged into it, and cables plug into each side of that T. 10-base-T, 100-base-T, 1000-base-T are all unshielded twisted pair, or UTP cables, which look a lot like thick phone cables, and they go from each computer to a hub or a switch. Initial numbers indicate the supported speed, so the 10 will stand for 10 megabits per second, and 1000 stands for 1000 megabits, also known as gigabit or 1 gigabit. 10-base-F cables are the same as 10-base-T, but they are fiber cables, and they'll transmit light pulses instead of electrical signals over copper. A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as its payload. An Ethernet frame is preceded by a preamble and start frame delimiter, or SFD, which are both part of the Ethernet packet at the physical layer, right? There are 4 types of Ethernet frames, and the most common one is the Ethernet 2 frame, also known as DICS frame. We're talking about the Ethernet 2 frame at the moment. Each Ethernet frame starts with an Ethernet header, which contains destination and source MAC addresses as its first 2 fields. The middle section of the frame is payload data, including any headers for other protocols, for example, Internet Protocol, carried in the frame. The frame ends with a frame check sequence, or FCS, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Probably the most well-known network layer protocol is, of course, IP, or Internet Protocol. As I mentioned in the beginning of the course, the Internet Protocol, or IP, is responsible for addressing hosts, encapsulating data into packets, or datagrams, including fragmentation and reassembly, and routing packets from a source host to a destination host across one or more IP networks. So like other Layer 3 protocols, IP is connectionless, which means it doesn't care whether the packet has reached the destination or not. That's what Layer 4 is for. All right? So there are 2 versions of IP that currently coexist within the global Internet: IP version 4, or IPv4, and IP version 6, or IPv6. IP addresses are made up of binary values and drive the routing of all data over the Internet. IPv4 addresses are 32 bits long, and IPv6 addresses are 128 bits long. Right now, we're going to see each of the versions in detail. But before we move on, let's compare the main features of each version. IPv4 is a 32-bit address, and IPv6 is a 128-bit address. Now, theoretically, you can address 2 to the power of 32 devices in IPv4, which is about 4.3 billion, right? In IPv6, on the other hand, you can address 2 to the power of 128 devices, which is, well, let's see. Why don't you just do the math on your own? So IPv4 is represented by the decimal equivalent of 4 octets, separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1, which means 255. So each octet can be any number from 0 to 255, right? Now, 128-bit IPv6 addresses are written using hexadecimal, as opposed to dotted decimal in IPv4. So because a hexadecimal number uses 4 bits, this means that an IPv6 address consists of 32 hexadecimal numbers. These numbers are grouped in 4s, giving 8 groups or blocks. The groups are written with a colon as a separator. Up to now, all the networks that we mentioned were assumed to be a public network, and all of the IP addresses were public IP addresses, right? In the Internet addressing architecture, a private network is a network that uses private IP address space. Wait. I'll try to explain an unknown with another one. But first, I should explain what the private IP address space is. Tell you what, let's take a break here, and I'll talk about the special use IP addresses, including the private IP address space. So the authorities, IETF and IANA, please don't ask. You can Google it if you really want to know who they are. But they've restricted from general use various reserved IP addresses for special purposes. So that means you cannot use any IP address in these reserved blocks as the public IP addresses of your devices. So here we have some of these reserved blocks. Now, these are the most important blocks for us to know, because pretty much anybody who's not familiar with the networking concept gets confused about the difference between public and private IP addresses. So these IP blocks are reserved for private networks. They're commonly used for home, office, and enterprise local area networks, or LANs. Private IP address spaces were originally defined in an effort to delay IPv4 address exhaustion, but they're also a feature of IPv6, where exhaustion is not an issue. Bear with me. Packets addresses in these ranges are not routable in the public internet because they are ignored by all public routers. Therefore, private hosts cannot directly communicate with public networks, but require network address translation, or NAT, at a routing gateway for this purpose. But no worries, we'll talk about NAT coming up next. So without getting too deep, the only thing about the loopback is that 127.0.0.1 is the most common IPv4 address which is mapped to the local host. So let me give you an example. The IP address of your host machine is 172.16.99.222, and a web application is served in your host. Now, in that machine, you can use the web address hhp://127.0.0.1 to access the web app, as well as hhp://172.16.99.222. Both IP addresses point to the same machine, which is your host. Generally, an IP address that starts with 169 means that your computer wasn't able to obtain an IP address from your DHCP server. Usually that means that your router is wedged and needs to be rebooted, or that your Wi-Fi isn't working at all. So now let's have a look at the private IP address blocks closely. As I mentioned a few minutes ago, a private network is a network that uses private IP address space. Administrators of private networks can assign networks and subnets from the above ranges. If an administrator decides to use the IP range 192.168.0.0/16 and then decides to have a single subnetwork assigning 255.255.0.0 as a subnet mask, then he or she will have a subnet with a max of 65,536 devices. Make sense? Internet Protocol version 4, IPv4, is one of the core protocols of standards-based networking methods on the Internet. It was described in IETF publication RFC 791 in 1981, and it was the first version deployed for production in the ARPANET in 1983. It still routes most internet traffic today despite the ongoing deployment of the successor protocol, IPv6. With IPv4, each address consists of 4 octets. Octet stands for 8-digit binary numbers. So an IPv4 address is 32 bits in total. So that means we can theoretically address 2 to the power of 32 devices with IPv4. So that means the address space of IPv4 is about 4.3 billion. Sounds like it's a big number, right? IPv4 is represented by the decimal equivalent of 4 octets separated by dots. The biggest number one can make with 8 binary digits is 2 to the power of 8 minus 1. That means 255. So each octet can be any number from 0 to 255. Now, also there are special meanings associated with 2 different ending numbers. In general, a last number of 0 stands for the network. Let's call that the base address. And a last number of 255 stands for all hosts on that network, called the broadcast address. Computers that are on the same local network share 3 of the 4 numbers. A computer can be on more than one network, so it can also have several names. Your patience pays off. Subnetting allows you to create multiple logical networks that exist within a single class A, B, or C network. If you do not subnet, you are only able to use one network from your class A, B, or C network, which is, well, pretty unrealistic. So subnetting is the process of designating some high-order bits from the host part as part of the network prefix and adjusting the subnet mask appropriately. So this divides a network into smaller subnets. In other words, in order to subnet a network, extend the natural mask with some of the high-order bits from the host ID portion of the address in order to create a subnetwork ID. So I'll give you an example. Let's take a Class C network of 192.168.2.0, which has a natural mask of 255.255.255.0. You can create subnets by moving 2 bits from the host part to the network prefix. Now, the last octet of the network mask starts with 11. So this 8-bit corresponds to 192 in decimal form. Now the network ID is 26-bit. In CIDR notation, it's now a /26 subnetwork. You can find the network prefix by a bitwise AND operation between the IP address and the subnet mask. The number of subnetworks available and the number of possible hosts in a network may be readily calculated. In our example, 2 bits were borrowed to create subnetworks, thus creating 2 to the power of 2 possible subnets. You with me? So now let's calculate the maximum number of hosts for each subnet. In our example, 26 bits are used to define the network. The remaining bits after the subnet bits are used for addressing hosts within the subnet. So, the host part of the IP address is 6-bit. All zeros and the all ones values for the host ID are not allowed in a subnetwork, right? These 2 values are reserved for the network address and broadcast address, respectively. So the maximum number of hosts which can be addressed in these subnetworks is 2 to the power of 6 minus 2, which equals 62. Excellent. So as a result, the IP addresses of the devices in the subnetwork 192.168.2.128/26 will be between 192.168.2.129 and 192.168.2.190. So introducing routing. IP MAC. So as you can see in the animation, routing is the process of transporting the packet received from a device over the network to a device in another network. Routers are at the core of the routing process, and routers don't care much about hosts. They only care about networks and the best way to reach all networks. while the IP address is used to carry the packet over the network and route it to the destination network in the best possible way, the MAC address is used to deliver the packet directed to the LAN of the destination, the host. In short, while routing is done with MAC address in local area networks, it is done with IP addresses outside of that local area network. Unicast, multicast, and broadcast. So in IPv4 addressing, there are broadcast patterns for devices to find or know about each other. So we're going to talk about 3 of these in pretty good detail. IP communication broadcasts, right? So the questions become, what is unicast and what is multicast and what is broadcast and what is IP-directed broadcasts? Well, they're all related, but they're definitely different. So we're going to split them up and take the answers one by one. All right, what is unicast? Well, if you look at the IPv4 address structure, each has a network partition and a host partition, right? Now, there are different ways to send packets from the source device, and these different transmissions affect the destination of these IPv4 addresses. Unicast transmission refers to one device sending a message to another device in a one-to-one communication. So the unicast packet has a destination IP address, which is the unicast address to a single receiver. Now, since the packet is generated from only one source, the source IP address can only be a unicast address. And this, by the way, applies to all, regardless of whether the destination IP address is unicast, broadcast, or multicast. So when you look at the picture on the screen, it consists of 3 hosts. You see, a printer and a router connected to a switch. Now, the animation is going to show the host with the IP address 172.16.4.1 sending a unicast packet to the IP address 172.16.4.253. So when the switch receives the frame, it forwards it to the printer with the IP address 172.16.4.253. IPv4 unicast host addresses are addresses in the range 1.1.1.1 to 223.255.255.255. However, like I said earlier, there are many addresses in this range that are reserved for special purposes. All right, Smarty Pants, so what's multicast? Multicast transmission reduces traffic by allowing a host to send a single packet to a selected group of hosts that subscribe to the multicast group. So a multicast packet is a packet whose destination IP address is a multicast address. So IPv4 reserved address is 224.0.0.0 all the way through 239.255.255.255 is a multicast range. So hosts receiving certain multicast packets are called multicast clients. These multicast clients use services requested by the client program to subscribe to the multicast group. Each multicast group is represented by a single IPv4 multicast destination address. So when an IPv4 host becomes a member of a multicast group, the host processes packets arriving at the multicast address and arriving at the individually allocated unicast address. Oh, yes. See, routing protocols such as OSPF use multicast transmissions. Yeah, for example, OSPF-enabled routers communicate with each other using the address 224.0.0.5, which is reserved for the OSPF multicast address. Only OSPF-enabled devices handle these packets with a destination IPv4 address of 224.0.0.5. All other devices ignore these packages. Okay, so what is broadcast? Well, broadcast transmission just refers to one device sending a message to all devices on the network in a one-to-all type of communication. Now, a broadcast packet is either all ones or 32 one-destination IP addresses in the host portion. Now, by the way, IPv4 uses broadcast packets. However, there are no broadcast packets in the next version up, IPv6. But you already knew that, right? Now, unicast packets must be handled by all devices in the same broadcast domain. Broadcast domains identify all hosts in the same network segment. So broadcast can be directed or limited. A directed broadcast is sent to all hosts on a given network. For example, a host on the 172.16.4.0/24 network sends a packet for 172.16.4.255. A limited broadcast is sent for 255.255.255.255. And by default, routers do not forward broadcasts. So broadcast packets do use resources on the network and allow each receiving host on the network to process this packet. Therefore, broadcast traffic should be limited so that the performance of the network or the devices is not adversely affected. So because routers allocate broadcast domains, dividing networks into subnets can improve network performance by eliminating excessive broadcast traffic. IP-directed broadcasts, yeah. Now, in addition to the broadcast address 255.255.255.255, there is a broadcast IPv4 address for each network. So this address is called a forwarded broadcast. It uses the highest address on the network. This is the address where all the host bits are 1. For example, the forwarded broadcast address for 192.168.1.0/24 is 192.168.1.255. So you see, this address provides communication to all hosts on that network. A host can send a single packet targeting the network's broadcast address to send data to all hosts on the network right from there. All right. Now, a device not directly connected to the target network will forward an IP-directed broadcast just as unicast IP packets are sent to a host on that network. So when a directed broadcast packet reaches a router directly connected to the target network, well, this packet is then broadcast to the target network. Oh, and by the way, due to security concerns and previous abuse by malicious users, routed broadcasts are turned off by default as of Cisco iOS version 12.0 with a global configuration command, no IP-directed broadcasts. Got it? All right, well, see, that's the lesson up to now. We've learned unicast, multicast, broadcast. Pretty cool, huh? So, see you in the next lesson. So the private addressing scheme works really well for computers that only have to access resources inside the network, like workstations needing access to file servers and printers and so forth. Routers inside the private network can route traffic between private addresses with no trouble whatsoever. However, to access resources outside the network, like the internet, for example, these computers need to have a public address so that responses to their requests return to them. Now this is where NAT comes into play. A workstation inside a private network makes a request to a computer on the internet. The switches or the routers within the network recognize that the request is not for a resource inside the network. So they send the request to the router, let's say the backbone router. Now, the backbone router sees the request from the computer with the internal IP. It then makes the same request to the internet using its own public address and returns the response from the internet resource to the computer inside the private network. From the perspective of the resource on the internet, it's sending information to the address of the router. From the perspective of the workstation, it appears that the communication is directly with the site on the internet. So when NAT is used like this, all users inside the private network that access the internet have the same public IP address. So that means only one public address is needed for hundreds or even thousands of users. So let's have a look and see how it works. Here's a typical home network. There's a laptop, desktop PC, and a smartphone, all connected to our home router. And the home router is, of course, connected to the internet. So when we register with our ISP, the Internet Service Provider, we get an IP address that is accessible throughout the internet, and that's pretty much assigned to that home router. We refer to it as real IP or public IP. Now suppose that the IP address 20.20.20.20 is assigned to our home router. Our devices inside the home network also have IP addresses, right? But in this case, they get private IP addresses, which are assigned by the home router and are not accessible from the internet. So as you can see here, the public IP addresses are red and the private IP addresses are green. So let's consider a connection request from the smartphone, which requests the homepage of abc.com. So to reach the page, the smartphone has to go through the home router. The packet has the source IP address and the source port address, as well as the destination IP address and the destination port. If it arrives at the web server with these values, it processes the request and tries to send the reply packet to the IP address 192.168.1.5. But that's unreachable for the web server because it's a private IP address. So, when the packet arrives at the home router, instead of sending the packet right over the internet, the home router changes the source IP address with its very own public IP address. It also creates a record in the NAT forwarding table. This table allows us to know which packets will be redirected to the smartphone when they come in. So moving right along, the packet travels over the internet and arrives at the web server. The web server creates a reply packet where the source IP address is itself and the destination IP address is the public IP address of the home router. When our home router receives a response, it looks at the NAT forwarding table and replaces the destination IP and the port according to the mapping inside the table. And finally, the smartphone receives the packet. Pretty cool, huh?
Wireshark, a tool used for creating and analyzing PCAP's network packet capture files, is commonly used as one of the best packet analysis tools. In this lecture, we will look at the basics of installing Wireshark and using it to perform basic packet analysis and take a deep look at each common networking protocol. If you have a general knowledge of networking basics, then you will be ready to begin. The installation for Wireshark is very easy and typically comes with a package GUI wizard. If you're using Kali Linux or the TryHackMe attack box, then it is already installed on your machine. Wireshark can run on Windows, MacOS, and Linux. To begin installing Wireshark on a Windows or MacOS device, you will need to first grab an installer from the Wireshark website. Once you have downloaded an installer, simply run it and follow the GUI wizard. If you are using Linux, you can install Wireshark with apt install Wireshark or a similar package manager. The first screen that we are greeted by when opening Wireshark is the main page that will allow us to specify our interface as well as apply filters to narrow down traffic that we are capturing. Here you can see that I have multiple interfaces to filter from. You may have more or fewer interfaces than I have. From here we can choose whether we want to perform a live capture on our interface or load a PC app for analysis. It is useful to note that the graphs next to the interface names show the activity on the interface. If an interface has a flat bar, it may be useless to attempt to capture on it, as no data on that interface is being picked up by the Wireshark client. If we begin by navigating to the green ribbon in Wireshark and select Manage Capture Filters, we can view a list of available filters. You do not have to select a filter. It will only help to bring down the number of packets being brought in and organize the capture. This is only a brief introduction to filters. For more information about filters, go to the Wireshark website. Once you have any capture filters you want selected, you can begin a capture on an interface by double-clicking the interface or by right-clicking and navigating to Start Capture. Depending on the network activity, you may see no packets coming in, or you may see packets streaming in very quickly. Once you're done gathering the packets you need or want, you can click the red square to stop capturing, and then you can begin your analysis. Looking at the screenshot, we see a sample capture. This screen is where you will do most of your analysis and dissection of packets. To open a packet capture, go to File, Open, and select what PCAP you want to analyze. From this screen, Wireshark gives us some important info about each packet, including packet number, time, source, destination, protocol, length, packet info. Along with quick packet information, Wireshark also color codes packets in order of danger level as well as protocol to be able to quickly spot anomalies in protocols and captures. This quick glance at packet information can be useful to track down exactly what you're looking for during analysis. Play around with the menus and various features of Wireshark to get a feel for it. Before going into detail about how to analyze each protocol in a PCAP, we need to understand the ways to gather a PCAP file. The basic steps to gather a PCAP in Wireshark itself can be simple, however, bringing into traffic in both the hard part as well as the fun part. This can include taps, port mirroring, MAC floods, and ARP poisoning. This lecture will not cover how to set up these various strategies of live packet capturing and will only cover the basic theory of each. Some things to think about before going headfirst into attempting to collect and monitor live packet capture. Begin by starting with a sample capture to ensure that everything is correctly set up and you are successfully capturing traffic. Ensure that you have enough compute power to handle the number of packets based on the size of the network. This will obviously vary network by network. Ensure enough disk space to store all of the packet captures. Once you meet all these criteria and have a collection method picked out, you can begin to actively monitor and collect packets on a network. Network taps are a physical implant in which you physically tap between a cable. These techniques are commonly used by threat hunting DAFR teams and red teams in an engagement to sniff and capture packets. Another option for planting a network tap would be an inline network tap, which you would plant between or inlines two network devices. The tap will replicate packets as they pass the tap. An example of this tap would be the very common throwing starline tap. McFloods are a tactic commonly used by red teams as a way of actively sniffing packets. McFlooding is intended to stress the switch and fill the CAM table. Once the CAM table is filled, the switch will no longer accept new MAC addresses, and so, in order to keep the network alive, the switch will send out packets to all ports of the switch. This technique should be used with extreme caution and with explicit prior consent. ARP poisoning is another technique used by red teams to actively sniff packets. By ARP poisoning, you can redirect the traffic from the host to the machine you're monitoring from. This technique will not stress network equipment. Like McFlooding, however, should still be used with caution and only if other techniques like network taps are unavailable. Packet filtering is a very important part of packet analysis, especially when you have a very large number of packets, sometimes even 100,000 plus. There is a second type of filter that is often thought of as more powerful and easier to use. The second method is known as display filters. You can apply display filters in two ways: through the Analyze tab and at the filter bar at the top of the packet capture. Filtering operator. Wireshark's filter syntax can be simple to understand, making it easy to get a hold of quickly. To get the most out of these filters, you need to have a basic understanding of Boolean and logic operators. Wireshark only has a few that you will need to be familiar with: an AND operator, or operator, equals operator, not equal operator, greater than operator, and less than operator. Wireshark also has a few other operators that go beyond the power of normal logical operators. These operators are the contains, matches, and bitwise in operators. These operators can be very useful when you have a large capture and need to pinpoint a single packet. Basic filtering. Filtering gives us a very large scope of what we can do with the packets. Because of this, there can be a lot of different filtering syntax options. We will only be covering the very basics in this lecture, such as filtering by IP, protocol, etc. There is a general syntax to the filter commands, however, they can be a little silly at times. The basic syntax of Wireshark filters is some kind of service or protocol like IP or TCP, followed by a dot, then whatever is being filtered, for example, an address, MAC, SRC, protocol, etc. Filtering by IP. The first filter we will look at is IP.AD.IR. This filter will allow you to comb through the traffic and only see packets with a specific IP address contained in those packets, whether it be from the source or destination. Syntax. IP address equal IP address. This filter can be handy in practical applications, say when you are threat hunting and have identified a potentially suspicious host with other tools. You can use Wireshark to further analyze the packets coming from that device. Filtering by SRC and DST. The second filter we'll look at is 2-in-1 as well as a filter operator, IP, CRC, and IP, DST. These filters allow us to filter the traffic by the source and destination from which the traffic is coming from. Syntax. IP source equal source IP address, and IP destination equal destination IP address. Similar to the first filter, we can see that Wireshark is combing through the packets and filtering based on the source and destination we set. Filtering by TCP protocols. The last filter that we will be covering is the protocol filter. This allows you to set a port or protocol to filter by and can be handy when trying to keep track of an unusual protocol or port being used. It is worthwhile to mention that Wireshark can filter by both port numbers as well as protocol names. Syntax. TCP port equal port or protocol name. Filtering by UDP protocols. You can also filter by UDP ports by changing the prefix from TCP to UDP. Syntax. UDP port equals port EI or protocol name. This section covers how Wireshark uses OSI layers to break down packets and how to use these layers for analysis. It is expected that you already have background knowledge of what the OSI model is and how it works. You can double-click on a packet in Capture to open its details. Packets consist of 5 to 7 layers based on the OSI model. We will go over all of them in an HTTP packet from a sample capture. Looking above, we can see 7 distinct layers to the packet: frame or packet, source MAC, source IP, protocol, protocol errors, application protocol, and application data. We will go over the layers in more detail. Frame layer 1. This will show you what frame packet you're looking at, as well as details specific to the physical layer of the OSI model. Source MAC layer 2. This will show you the source and destination MAC addresses from the data link layer of the OSI model. Source IP layer 3. This will show you the source and destination IPv4 addresses from the network layer of the OSI model. Protocol layer 4. This will show you details of the protocol, used UDP or TCP, along with source and destination ports from the transport layer of the OSI model. Application protocol layer 5. This will show details specific to the protocol being used, such HTTP, FTP, SMB, etc., from the application layer of the OSI model. Application data. This is an extension of layer 5 that can show the application-specific data. Now that we understand what a general packet is composed of, move on to looking at various application protocols and their specific details. Learn the basics of Wireshark and how to analyze protocols and PCAP. Wireshark is an open-source, cross-platform network packet analyzer tool capable of sniffing and investigating live traffic and inspecting packet captures, PCAP. It is commonly used as one of the best packet analysis tools. In this lecture, we will look at the basics of Wireshark and use it to perform fundamental packet analysis. Wireshark is one of the most potent traffic analyzer tools available in the wild. There are multiple purposes for its use: detecting and troubleshooting network problems, such as network load failure points and congestion; detecting security anomalies, such as rogue hosts, abnormal port usage, and suspicious traffic; investigating and learning protocol details, such as response codes and payload data. Wireshark GI opens with a single all-in-one page, which helps users investigate the traffic in multiple ways. At first glance, 5 sections stand out. Toolbar. The main toolbar contains multiple menus and shortcuts for packet sniffing and processing, including filtering, sorting, summarizing, exporting, and merging. Display filter bar. The main query and filtering section. Recent files, list of the recently investigated files. You can recall listed files with a double click. Capture filter and interfaces. Capture filters and available sniffing points network interfaces. The network interface is the connection point between a computer and a network. The software connection, a GLOO, Ethernet, and ENS enables networking hardware. Status bar. Tool status, profile, and numeric packet information. Loading PCAP files. Let's load that file and see Wireshark's detailed packet presentation. Note that you can also use the File menu, dragging and dropping the file, or double-clicking on the file to load a PCAP. Now we can see the processed file name, detailed number of packets, and packet detail. Packet details are shown in 3 different panes, which allow us to discover them in different formats. Packet list panel. Summary of each packet, a source and destination addresses, protocol, and packet info. You can click on the list to choose a packet for further investigation. Once you select a packet, the details will appear in the other panels. Packet details panel. Detailed protocol breakdown of the selected packet. Packet bytes panel. Hex and decoded ASC2 representation of the selected packet. It highlights the packet field depending on the clicked section in the details panel. Coloring packets. Along with quick packet information, Wireshark also color packets in order of different conditions and the protocol to spot anomalies in protocols and captures quickly. This explains why almost everything is green in the given screenshots. This glance at packet information can help track down exactly what you're looking for during analysis. You can create custom color rules to spot events of interest by using display filters, and we will cover them in the next lecture. Now let's focus on the defaults and understand how to view and use the represented data detail. Wireshark has two types of packet coloring methods: temporary rules that are only available during a program session and permanent rules that are saved under the preference file profile and available for the next program session. You can use the right-click menu or View Coloring Rules menu to create permanent coloring rules. The Colorees Packet List menu activates or deactivates the coloring rule. Temporary packet coloring is done with the right-click menu or View Conversation Filter menu, which is covered in Lecture, the Packet Filtering. The default permanent coloring is shown Traffic Sniffing. You can use the blue shark button to start network sniffing, capturing traffic. The red button will stop the sniffing, and the green button will restart the sniffing process. The status bar will also provide the used sniffing interface and the number of collected packets. View file detail. Knowing the file details is helpful, especially when working with multiple PCAP files. Sometimes you will need to know and recall the file details like file hash, capture time, capture file comments, interface, and statistics to identify the file, classify and prioritize it. You can view the details by following statistics, capture file properties, or by clicking the PCAP icon located on the left bottom of the window. Packet navigation. Packet numbers. Wireshark calculates the number of investigated packets and assigns a unique number for each packet. This helps the analysis process for big captures and makes it easy to go back to a specific point of an event. Go to Packet. Packet numbers do not only help to count the total number of packets or make it easier to find, investigate specific packet. This feature not only navigates between packets up and down, it also provides in-frame packet tracking and finds the next packet in the particular part of the conversation. You can use the Go menu and toolbar to view specific packets. Find packets. Apart from packet number, Wireshark can find packets by packet content. You can use the Edit, Find Packet menu to make a search inside the packets for a particular event of interest. This helps analysts and administrators to find specific intrusion patterns or failure traces. There are two crucial points in finding packets. The first is knowing the input type. This functionality accepts 4 types of inputs: display filter, hex, string, and reject. String and reject searches are the most commonly used search types. Searches are case insensitive, but you can set the case sensitivity in your search by clicking the radio button. The second point is choosing the search field. You can conduct searches in the 3 panes: packet list, packet details, and packet bytes. And it is important to know the available information in each pane to find the event of interest. For example, if you try to find the information available in the packet details pane and conduct the search in the packet list pane, Wireshark won't find it even if it exists. Mark packets. Marking packets is another helpful functionality for analysts. You can point to a specific packet for further investigation by marking it. It helps analysts point to an event of interest or export particular packets from the capture. You can use the Edit or the right-click menu to mark. Unmarked packets. Marked packets will be shown in black regardless of the original color, representing the connection type. Note that marked packet information is renewed every file session, so marked packets will be lost after closing the capture file. Packet comments. Similar to packet marking, commenting is another helpful feature for analysts. You can add comments for particular packets that will help the further investigation or remind and point out important suspicious points for other layer analysts. Unlike packet marking, the comments can stay within the capture file until the operator removes them. Export packets. Capture files can contain thousands of packets in a single file. As mentioned earlier, Wireshark is not an IDS, so sometimes it is necessary to separate specific packages from the file and dig deeper to resolve an incident. This functionality helps analysts share the only suspicious packages decided scope. Thus, redundant information is not included in the analysis process. You can use the File menu to export packets. To report objects, you're on saying. Wireshark can extract files transferred through the wire. For a security analyst, it is vital to discover shared files and save them for further investigation. Exporting objects are available only for selected protocol streams like DICOM, HTTP, IMF, SMB, and TFTP. Time display format. Wireshark lists the packets as they are captured, so investigating the default flow is not always the best option. By default, Wireshark shows the time in seconds since beginning of capture. The common usage is using the UTC time display format for a better view. You can use the View Time Display Format menu to change the time display format. Expert Info. Wireshark also detects specific states of protocols to help analysts easily spot possible anomalies and problems. Note that these are only suggestions, and there is always a chance of having false positives, negatives. Expert Info can provide a group of categories in 3 different severities. Chat Blue. Information on usual workflow. Note Cyan. Notable events like application error codes. Warn Yellow. Warnings like unusual error codes or problem statements. Error Red. Problems like malformed packets. You can use the lower left bottom section in the status bar or Analyze Expert Information menu to view all available information entries via a dialog box. It will show the packet number, summary, group protocol, and total occurrence. Packet filtering. Wireshark has a powerful filter engine that helps analysts to narrow down the traffic and focus on the event of interest. Wireshark has 2 types of filtering approaches. Capture and display filters. Capture filters are used for capturing only the packets valid for the used filter. Display filters are used for viewing the packets valid for the used filter. Filters are specific queries designed for protocols available in Wireshark's official protocol reference. While the filters are only the option to investigate the event of interest, there are 2 different ways to filter traffic and remove the noise from the capture file. The first one uses query, and the second uses the right-click menu. Wireshark provides a powerful GUI, and there is a golden rule for analysts who don't want to write queries for basic tasks. If you can click on it, you can filter and copy it. Apply as filter. This is the most basic way of filtering traffic. While investigating a capture file, you can click on the field you want to filter and use the right-click menu or Analyze, add Apply as Filter menu to filter the specific value. Once you apply the filter, Wireshark will generate the required filter query, apply it, show the packets according to your choice, and hide the unselected packets from the packet list pane. Note that the number of total and displayed packets are always shown on the status bar. Conversation filter. When you use the Apply as a Filter option, you will filter only a single entity of the packet. This option is a good way of investigating a particular value in packets. However, suppose you want to investigate a specific packet number and all linked packets by focusing on IP addresses and port numbers. In that case, the Conversation Filter option helps you view only the related packets and hide the rest of the packets easily. You can use the right-click menu or Analyze Conversation Filter menu to filter conversations. Colors conversation. This option is similar to the conversation filter with one difference. It highlights the linked packets without applying a display filter and decreasing the number of viewed packets. This option works with the coloring rules option and changes the packet colors without considering the previously applied color rule. You can use the right-click menu or View Color as Conversation menu to colorize a linked packet in a single click. Note that you can use the View Colorize Conversation Reset Colorization menu to undo this operation. Prepare as Filter. Similar to Apply as Filter, this option helps analysts create display filters using the right-click menu. However, unlike the previous one, this model doesn't apply the filters after the choice. It adds the required query to the pane and waits for the execution command to enter or another chosen filtering option by using the NA or from the right-click menu. Applies column. By default, the packet list pane provides basic information about each packet. You can use the right-click menu or Analyze Apply as Column menu to add columns to the packet list pane. Once you click on a value and apply it as a column, it will be visible on the packet list pane. This function helps analysts examine the appearance of a specific value field across the available packets in the capture file. You can enable disable the columns shown in the packet list pane by clicking on the top of the packet list pane. Follow stream. Wireshark displays everything in packet portion size. However, it is possible to reconstruct the streams and view the raw traffic as it is presented at the application level. Following the protocol, streams help analysts recreate the application level data and understand the event of interest. It is also possible to view the unencrypted protocol data like usernames, passwords, and other transferred data. You can use the right-click menu or Analyze Follow TCP UDP HTTP stream menu to follow traffic streams. Streams are shown in a separate dialog box. Packets originating from the server are highlighted with blue, and those originating from the client are highlighted with red. Once you follow a stream, Wireshark automatically creates and applies the required filter to view the specific stream. Remember, once a filter is applied, the number of the viewed packets will change. You will need to use the X button located on the right upper side of the display filter bar to remove the display filter and view all available packets in the capture file. Wireshark. Packet operations. Learn the fundamentals of packet analysis with Wireshark. Introduction. In this lecture, we will cover the fundamentals of packet analysis with Wireshark and investigate the event of interest at the packet level. In this lecture, we will cover advanced features of the Wireshark by focusing on packet-level details with Wireshark statistics, filters, operators, and functions. Statistics. This menu provides multiple statistics options ready to investigate to help users see the big picture in terms of the scope of the traffic, available protocols, endpoints and conversations, and some protocol-specific details like DHCP, DNS and HTTP2. For a security analyst, it is crucial to know how to utilize the statistical information. This section provides a quick summary of the processed PCAP, which will help analysts create a hypothesis for an investigation. You can use the statistics menu to view all available options. Resolved addresses. This option helps analysts identify IP addresses and DNS names available in the capture file by providing the list of the resolved addresses and their host names. Note that the hostname information is taken from DNS answers in the capture file. Analysts can quickly identify the accessed resources by using this menu. Thus, they can spot accessed resources and evaluate them according to the event of interest. You can use the Statistics Resolved Addresses menu to view all resolved addresses by Wireshark. Protocol Hierarchy. This option breaks down all available protocols from the capture file and helps analysts view the protocols in a tree view based on packet counters and percentages. Thus, analysts can view the overall usage of the ports and services and focus on the event of interest. The golden rule mentioned in the previous lecture is valid in this section. You can right-click and filter the event of interest. You can use the Statistics Protocol Hierarchy menu to view this info. Conversations. Conversation represents traffic between two specific endpoints. This option provides the list of the conversations in 5 base formats: Ethernet, IPv4, IPv6, TCP, and UDP. Thus, analysts can identify all conversations and contact endpoints for the event of interest. You can use the Statistic Conversations menu to view this info. Endpoints. The Endpoints option is similar to the Conversations option. The only difference is that this option provides unique information for a single information field like Ethernet IPv4, IPv6, TCP, and UDP. Thus, analysts can identify the unique endpoints in the capture file and use it for the event of interest. You can use the Statistics Endpoints menu to view this info. Wireshark also supports resolving MAC addresses to human-readable format using the manufacturer name assigned by IEEE. Note that this conversion is done through the first 3 bytes of the MAC address and only works for the known manufacturers. When you review the Ethernet endpoints, you can activate this option with the Name Resolution button. Name resolution is not limited only to MAC addresses. Wireshark provides IP and port name resolution options as well. However, these options are not enabled by default. If you want to use these functionalities, you need to activate them through the Edit. Preferences, Name Resolution menu. Once you enable IP and port name resolution, you will see the resolved IP address and port names in the packet list pane, and also will be able to view resolved names in the conversations and endpoints menus as well. Statistics, protocol details, IPv4 and IPv6. Up to here, almost all options provided information that contain both versions of the IP addresses. The Statistics menu has 2 options for narrowing the statistics on packets containing a specific IP version. Thus, analysts can identify and list all events linked to specific IP versions in a single window and use it for the event of interest. You can use the Statistics IPv6 Statistics menu to view this info. DNS. This option breaks down all DNS packets from the capture file and helps analysts view the findings in a tree view based on packet counters and percentages of the DNS protocol. Thus, analysts can view the DNS service overall usage, including recode, opcode, class, query type, service and query stats, and use it for the event of interest. You can use the Statistics DNS menu to view this info. HTTP. This option breaks down all HTTP packets from the capture file and helps analysts view the findings in a tree view based on packet counters and percentages of the HTTP protocol. Thus, analysts can view the HTTP service's overall usage, including request and response codes and the original request. You can use the Statistics HTTP menu to view this info. Packet filtering principles. In this lecture, we will use queries to filter packets. As mentioned earlier, there are two types of filters in Wireshark. While both use similar syntax, they are used for different purposes. Let's remember the difference between these two categories. Capture filters. This type of filter is used to save only a specific part of the traffic. It is set before capturing traffic and not changeable during the capture. Display filters. This type of filter is used to investigate packets by reducing the number of visible packets, and it is changeable during the capture. Note, you cannot use the display filter expressions for capturing traffic. The typical use case is capturing everything and filtering the packets according to the event of interest. Only experienced professionals use capture filters and sniffing traffic. This is why Wireshark supports more protocol types in display filters. These ensure you thoroughly learn how to use capture filters before using them in a live environment. Remember, you cannot capture the event of interest if your capture filter is not matching the specific traffic pattern you are looking for. Capture filter syntax. These filters use byte offsets, hex values, and masks with Boolean operators, and it is not easy to predict the filter's purpose at first glance. The base syntax is explained below. Scope, host, net, port, and port range. Direction, SRC, DST, SIC, or DST, SRC, and DST. Protocol, either WAN IP, IP6, AREP, RARP, TCP, and UDP. Sample filter to capture port 80 traffic, TCP, port 80. A quick reference is available under the Capture Filters menu. Display filter syntax. This is Wireshark's most powerful feature. It supports 3,000 protocols and allows conducting packet-level searches under the protocol breakdown. The official display filter reference provides all supported protocols breakdown for filtering. Sample filter to capture port 80 traffic. DCP.port equals 80. Now let's understand the fundamentals of the display filter operations. A quick reference is available under the Analyze. Display filters menu. Comparison operators. You can create display filters by using different comparison operators to find the event of interest. The primary operators are shown in the table. Description. Equal, not equal, greater than, less than, greater than or equal to, less than or equal to. Note, Wireshark supports decimal and hexadecimal values in filtering. You can use any format you want according to the search you will conduct. Logical expressions. Wireshark supports Boolean syntax. You can create display filters by using logical operators. Description, logical and, logical or, logical not. Packet filter toolbar. The filter toolbar is where you create and apply your display filters. It is a smart toolbar that helps you create valid display filters with ease. Before starting to filter packets, here are a few tips. Packet filters are defined in lowercase. Packet filters have an autocomplete feature to break down protocol details, and each detail is represented by a dot. Packet filters have a three-color representation explained: green, valid filter; invalid filter; yellow, warning filter. This filter works, but it is unreliable, and it is suggested to change it with a valid filter. Packet filtering, protocol filters. Wireshark supports 3,000 protocols and allows packet-level investigation by filtering the protocol fields. This task shows the creation and usage of filters against different protocol fields. IP filters help analysts filter the traffic according to the IP-level information from the packet's network layer of the OSI model. This is one of the most commonly used filters in Wireshark. These filters filter network-level information like IP addresses, version, time to live, type of service, flags, and checksum values. The common filters are shown in the given table. Filter and description. IP show all IP packets. IP.addr equals IP address. Show all packets containing IP address. IP.addr equals IP address. Subnet EH show all packets containing IP addresses from subnet. IP.src equals IP address. Show all packets originated from IP address. IP.dst equals IP address. Show all packets sent to IP address. IP.addrvs IP.sirc or IP.dst. The IP.addr filters the traffic without considering the packet direction. The IP.sdrc or IP.dst filters the packet depending on the packet direction. TCP and UDP filters. TCP filters help analysts filter the traffic according to protocol-level information from the packet's transport layer of the ASI model. These filters filter transport protocol-level information like source and destination ports, sequence number, acknowledgement number, window size, timestamps, flags, length, and protocol errors, filter, and description. Filter and expression. TCP.port equals 80. Show all TCP packets with port 80. TCP.src port 80. Show all TCP packets originating from port 80. TCP.dst port 80. Show all TCP packets sent to port 80. UDP.port 443. Show all UDP packets with port 443. UDP.src port 443. Show all UDP packets originating from port 443. UDP.dist port 443. Show all UDP packets sent to port 443. Application-level protocol filters. HTTP and DNS. Application-level protocol filters help analysts filter the traffic according to application protocol-level information from the packet's application layer of the OSI model. These filters filter application-specific information like payload and linked data depending on the protocol type. Filter and description. HTTP. Show all HTTP packets. HTTP.response.code 200. Show all packets with HTTP response code 200. HTTP.request.method get. Show all HTTP get requests. HTTP.request.method post. Show all HTTP post requests. DNS. Show all DNS packets. DNS.flags.response0. Show all DNS requests. DNS.flags.response1. Show all DNS responses. DNS.cry.type1. Show all DNSA records. Display filter expressions. As mentioned earlier, Wireshark has a built-in option display filter expression that stores all supported protocol structures to help analysts create display filters. When an analyst can't recall the required filter for a specific protocol or is unsure about the assignable values for a filter, the Display Filter Expressions menu provides an easy-to-use display filter builder guide. It is available under the Analyze Display Filter Expression menu. It is impossible to memorize all details of the display filters for each protocol. Each protocol can have different fields and can accept various types of values. The Display Filter Expressions menu shows all protocol fields, accepted value types, integer or string, and predefined values, if any. Note that it will take time and require practice to master creating filters and learning the protocol filter field. Advanced filtering. So far, you have learned the basics of packet filtering operations. Now, it is time to focus on specific packet details for the event of interest. Wireshark has advanced operators and functions. These advanced filtering options help the analyst conduct an in-depth analysis of an event of interest. Filter contains type comparison operator, search a value inside packet. It is case-sensitive and provides similar functionality to the find option by focusing on a specific field. Example, find all website host. List all HTTP packets where packets host field contains the website keyword. Usage http.host contains website. Filter matches. Type comparison operator. Search a pattern of irregular expression. It is case insensitive and complex queries have a margin of error. Example, find all get. List all HTTP packets where packets http.request.method fields match keywords get. Usage http.requests.method matches get. Filter and/or search a value or field inside of a specific value. Example, Find all packets that use ports 80 or 443. List all TCP packets where packets port fields have values 80 or 443. Usage, tcp.port80 or tcp.port443. Filter, upper. Convert a string value to uppercase. Example, find all website host. Convert all HTTP packets host fields to uppercase and list packets that contain the website keyword. Usage, upper http.host contains website. Filter, lower. Convert a string value to lowercase. Example, find all website host. Convert all HTTP packets host fields info to lowercase and list packets that contain the website keyword. Usage, lower TCP.host contains website. Filter, string. Convert a non-string value to a string. Example, find all frames with even numbers. Convert all frame number fields to string values and list frames end with even values. Usage, string frame.number matches, 24,680 bookmarks and filtering buttons. We've covered different types of filtering options, operators, and functions. It is time to create filters and save them as bookmarks and buttons for later usage. As mentioned in the previous task, the filter toolbar has a filter bookmark section to save user-created filters, which helps analysts reuse favorite complex filters with a couple of clicks. Similar to bookmarks, you can create filter buttons ready to apply with a single click. Creating and using bookmarks. Creating and using display filter button. Profiles. Wireshark is a multifunctional tool that helps analysts to accomplish in-depth packet analysis. As we covered during the lecture, multiple preferences need to be configured to analyze a specific event of interest. It is cumbersome to rechange the configuration for each investigation case, which requires a different set of coloring rules and filtering buttons. This is where Wireshark profiles come into play. You can create multiple profiles for different investigation cases and use them accordingly. You can use the Edit, Configuration Profiles menu or the lower right bottom of the status bar. Profile section to create, modify, and change the profile configuration.
Internet Control Message Protocol, ICMP, is an error reporting protocol that network devices like routers use to generate error messages to the source IP address when network problems prevent delivery of IP packets. ICMP messages are sent in several situations. For example, when a datagram cannot reach its destination, when the gateway does not have the buffering capacity to forward a datagram, and when the gateway can direct the host to send traffic on a shorter route. The Internet Protocol is not designed to be absolutely reliable. I'll explain why. Hold on. The purpose of these control messages is to provide feedback about problems in the communication environment, not to make IP reliable. There's still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any report of their loss. The higher-level protocols that use IP must implement their own reliability procedures if reliable communication is required. So the ICMP header starts after the IPv4 header. All ICMP packets have an 8-byte header and variable size data section. The first 4 bytes of the header have a fixed format, while the last 4 bytes depend on the type and code of that ICMP packet. ICMP type and code in the header identifies the control message. Some of the ICMP control messages are shown in this slide. So ping is the most well-known application of the ICMP. It operates by sending ICMP echo request packets to the target host and then waiting for an ICMP echo reply.
ICMP traffic. ICMP overview. ICMP, or Internet Control Message Protocol, is used to analyze various nodes on a network. This is most commonly used with utilities like ping and Traceroute. You should already be familiar with how ICMP works. You can see a sample of what a ping would look like. We can see a request to the server from ICMP, then a reply from the server, ICMP traffic overview, ICMP request. We see packet details for a ping request packet. There are a few important things within the packet details that we can take note of, first being the type and code of the packet. A type that equals 8 means that it is a request packet. If it is equal to 0, it is a reply packet. When these codes are altered or do not seem correct, that is typically a sign of suspicious activity. There are two other details within the packet that are useful to analyze: timestamp and data. The timestamp can be useful for identifying the time the ping was requested. It can also be useful to identify suspicious activity in some cases. We can also look at the data string, which will typically just be a random data string. ICMP reply. You can see that the reply packet is very similar to the request packet. One of the main differences that distinguishes a reply packet is the code. In this case, you can see it is 0, confirming that it is a reply packet. The same analysis techniques for request packets apply here as well. Again, the main difference will be the packet type.
All right, hello, my friends. Let's have a look at this ICMP messaging with Wireshark. We can observe the traffic in more detail, and to do this, let's ping another computer on the same local network. So we're sending a ping message to another computer with an IP address of 192.168.1.35 on the same network. Of course, we need to put Wireshark into listening mode before we send this message, right? So we'll press the Wireshark start button and start listening. So you type in ping 192.168.1.35 in the command prompt window and press enter. When the ping process is finished, we can press the Wireshark stop button to finish listening. Yeah, so let's not increase the number of packets. 4 ping ICMP messages, gone and back again. And the first ping is 3 milliseconds, and the other 3 are 1 millisecond ICMP messages. Okay, good. So now let's examine this traffic with Wireshark. Let's write ICMP for the filter, and we've listed 8 ICMP messages after the filter. Request, reply, we actually listed 4 ping messages. Ethernet 2, source MAC address 0068 EB5 BD5 3F, destination MAC address 001F D015 E241. Source IP address 192.168.1.34. Destination IP is 168.1.35. Type equals 8. Requests. And see reply type equals 0 here. Right, so let's see this ICMP message traffic in graphic form. Here we can choose statistics flow graph. Remember, our computer is 192.168.1.34, and where did we ping? On the IP address 192.168.1.35. Good, so let's look at the arrows in the graph, and there it is 4 times. And from here, you can better visualize the ping message traffic, seeing it in the graph. Very good, my friends. Thanks for hanging in there.
ARP traffic. ARP, or Address Resolution Protocol, is a Layer 2 protocol that is used to connect IP addresses with MAC addresses. They will contain request messages and response messages. To identify packets, the message header will contain one of 2 operations: request, reply. You can see a packet capture of multiple ARP requests and replies. It is useful to note that most devices will identify themselves. An example of suspicious traffic would be many requests from an unrecognized source. You need to enable a setting within Wireshark, however, to resolve physical addresses. To enable this feature, navigate to View and Name Resolution. Ensure that Resolve Physical Addresses is checked. ARP Traffic Overview. ARP Request Packets. We can begin analyzing packets by looking at the first ARP request packet and looking at the packet details. Looking at the screenshot, we can see that a device is sending our IP requests, meaning that we should be able to trust this device. However, you should always stay on the side of caution when analyzing packets. ARP reply packet. Looking at the packet details, we can see from the opcode that it is an ARP reply packet. We can also get other useful information like the MAC and IP address that was sent along with the reply, since this is a reply packet. We know that this was the information sent along with the message. ARP is one of the simpler protocols to analyze. All you need to remember is to identify whether it is a request or reply packet and who it is being sent by. ARP protocol, or Address Resolution Protocol, is the technology responsible for allowing devices to identify themselves on a network. Address Resolution Protocol poisoning, also known as ARP spoofing or man-in-the-middle attack, is a type of attack that involves network jamming. manipulating by sending malicious ARP packets to the default gateway. The ultimate aim is to manipulate the IP to MAC address table and sniff the traffic of the target host. There are a variety of tools available to conduct ARP attacks. However, the mindset of the attack is static, so it is easy to detect such an attack by knowing the ARP protocol workflow and Wireshark skills. ARP analysis, in a nutshell, works on the local network, enables the communication between MAC addresses, not a secure protocol, not a routable protocol. It doesn't have an authentication function. Common patterns are request to response, announcement, and gratuitous packets. Before investigating the traffic, let's review some legitimate and suspicious ARP packets. Global search, ARP. ARP options. Opcode 1, ARP request. Opcode 2, ARP responses. ARP scanning. Possible ARP poisoning detection. Possible ARP flooding from detection. A suspicious situation means having two different ARP responses conflict for a particular IP address. In that case, Wireshark's Expert Info tab warns the analyst. However, it only shows the second occurrence of the duplicate value to highlight the conflict. Therefore, identifying the malicious packet from the legitimate one is the analyst's challenge. A possible IP spoofing case is shown in the picture. Here, knowing the network architecture and inspecting the traffic for a specific time frame can help detect the anomaly. As an analyst, you should take notes of your findings before going further. This will help you be organized and make it easier to correlate the further finding. Look at the given picture. There is a conflict. The MAC address crafted an ARP request with the IP address, then claimed to have the same IP address.
Hello, my friends. We're going to analyze the ARP protocol with Try Hack Me Wireshark. So let's go ahead and observe a few more of the detailed results. From the IP address of 10.10.159.142, our very own computer, let's send 5 ping messages to a computer with an IP address of 10.10.136.117. It's going to be a different computer on this same network. All right, so let's type in the command prompt. The MAC address of the target computer is going to be required for communication. And because the source cannot send an ICMP message without the destination's device's MAC address, we will first need to press the Wireshark start button and listen out for it. So we'll type ping-c5 10.10.136.117 right here in the command prompt and press enter. So it'll return 5 pings, and we can stop listening with the Wireshark stop button. All right, so we see the results of the 5 ping messages in the command prompt window. Ping results are listed with a lot of detail. The timings of the 5 ping messages can be examined and compared as well. What we're going to do is analyze this traffic with Wireshark. So we made Wireshark full screen here. And let's make an ARP filter from within the network traffic. So when we make an ARP filter, we see 2 ARPs in protocols 1821 and 1822. The IP address of our computer is 10.10.159.142, but who are we pinging? 10.10.136.117. So the MAC address of this IP address is being asked for with ARP, my friends, you see, and it does indeed broadcast, just like we were talking about earlier. It also has its destination here. Broadcast is written as the destination, right? It actually broadcasts to the whole network. It says the protocol is ARP, and here the MAC addresses are written. Yeah. So it already starts with numbers 0 and 2, so 2 computers on the same local network. So traffic MAC address 1821 is our computer's MAC address, 02545E7186A5. And the traffic numbered 1822 is the MAC address of the destination computer 10.10.136.117 IP address, and the MAC address 028C34F0B5DD. So why don't we just examine here in the package details section, 1821 ARP request and the 1822 ARP reply. So let's have a look at the first one from 1821, my friends. Here we've got Ethernet 2. The MAC address of the source in layer 2 is 02545E7186A5. The source address is 10.10.159.142. Just happens to be the address of our computer. Now, if the destination MAC address is the highest 48-bit MAC address, the highest value is FFFFFFFF, right? But the largest number you know is the hexadecimal F. That is the highest value, and it's written MAC. So it already has been given in detail in Ethernet 2 line here. Distribution broadcast, FFFFFFFFF. Now let's have a look at the ARP request content in detail. So here's our IPv4 address, opcode equals 1. And in the answer, we will see that it is 2. So this is also an important issue here, right? So here's the sender's IP address. That is a part that belongs to our computer. Okay, the target is 10.10.136.117. That's the IP address. The MAC address is empty. 000000000000. Now, why is it empty? Yeah, we don't know the ARP request already. That's why it's empty. Good guess if you were guessing. Anyway, let's click on the reply, traffic number 1822. And what does that say? Well, let's have a look. We're looking at the details of the address resolution protocol reply. And this time the sender and destination have changed places. Also, this has changed, right? Opcode equals 2. Now, since the reply came from the other computer, the location of the sender and the target has changed as well. That makes sense. Sender IP address, 10.10.136.117. The sender MAC address, 028C34F0B5DD. So the target was back to our computer, 10.10.159.142, which is the IP address. And of course, our destination MAC address is 0254-5E7186A5. So how does it actually know? Well, because in the ARP request, we sent our MAC address. It has saved our MAC address in the ARP table. Now this in return, the reply doesn't have to be broadcast, right? It's unicast because the destination MAC address is known. So we received the ARP request response, sent the MAC address of 10.10.136.117, and ARP is now finished. Now let's have a look at a graphical representation of the ARP traffic, my friends. So we'll choose the statistics flow graph menu and the graphic display, as you can see. So we can choose limit to display filter and ARP traffic will fill the screen. Now look at this. If you remember, 0254-5E7186A5 is the MAC address of our computer. So what are you actually asking? The MAC address of 10.10.136.117. So see, it's first broadcast. So we see the broadcast, and here the target is the full network. Of course, who the reply comes from, the computer with the IP address of 10.10.136.117. And other computers or other devices in the network need not reply, and so they don't take any action. Now here too, first line in the comments, 10.10.136.117. Who are you? 10.10.159.142 is asking. So the reply comes from the computer with the address, the IP address of 10.10.136.117 in the second comment line. And it writes its own MAC address, 028C34F0B5DD, and sends it in the reply. So you see that the graph is actually a great way to have a look. It's well illustrated by the arrows in the request and the reply. Broadcast in the middle because, well, the request doesn't actually know the direct MAC address, so it has to send it out throughout the network, and the reply is unicast as long as the destination MAC is known. So directly from this MAC to MAC. Okay, so source MAC address is known, destination MAC address is known, and the graphics are already MAC address based. So these arrows point to the MAC addresses, and it already works with layer 2 MAC addresses. Switches find direction with the MAC address. So let's close up this graph window and let's see where are our pings. Now 1821, 1822 ARP. So I couldn't see ICMP. So we'll do an ICMP filter. And sure enough, ICMP was able to start in 1823. And it was sent from 10.10.159.142 to 10.10.136.117 from our computer. And how many messages? 5 units. receive requests and replies. So where were the ARP packets? 1821 and 1822 numbers in the ARP. So let's see it all together. Okay, so look at this. The ARP is here. ICMP will be possible after the ARP is done. It's not possible otherwise, you remember. So in other words, you cannot send data on a local network without knowing the MAC addresses. All right? It's just not possible, and that's a good thing, my friends. All right, so there's just about everything you need to know about ARP. We can wrap it up here. I'll see you next time.
The Transmission Control Protocol, TCP, provides a communication service at an intermediate level between an application program and the Internet Protocol. It provides host-to-host connectivity at the transport layer of the Internet model. TCP works with the Internet Protocol, IP, which defines how computers send packets of data to each other. Together, TCP and IP are basic rules defining the Internet. TCP is a connection-oriented protocol, which means a connection is established and maintained until the application programs at each end have finished exchanging messages. It determines how to fragment application data into packets that networks can deliver, sends packets to and accepts packets from the network layer, manages flow control, and, because it is meant to provide error-free data transmission, handles retransmission of dropped or garbled packets, as well as acknowledgement of all packets that arrive. Let's see the connection-oriented error-free communication of TCP in an example. When a web server sends an HTML file to a client, it uses the HTTP protocol to do so. The HTTP program layer asks the TCP layer to set up the connection and send the file. The TCP stack divides the file into packets, numbers them, and then forwards them individually to the IP layer for delivery. Although each packet in the transmission will have the same source and destination IP addresses, packets may be sent along multiple routes. The TCP program layer in the client computer waits until all of the packets have arrived, then acknowledges those it receives and asks for the retransmission on any it does not, based on missing packet numbers. Then assembles them into a file and delivers the file to the receiving application. The TCP three-way handshake is the method used by TCP to set up a connection. TCP's three-way handshaking technique is often referred to as SYN, SYNAC, ACK, because there are three messages transmitted by TCP to negotiate and start a TCP session between two computers. This three-way handshake process is also designed so that both ends can initiate and negotiate separate TCP socket connections at the same time. That means the connection is full duplex. Oh, you know what? We have to take a break at this point and talk about TCP flags. There are 1-bit flags in TCP headers, which are called TCP flags. TCP flags are used within TCP packet transfers to indicate a particular connection state or provide additional information. Ignoring ECE, CWR, and NS flags for now, there are basically 6 TCP flags. The SYN, or synchronization flag, is used as a first step in establishing a three-way handshake between two hosts. Only the first packet from both the sender and the receiver should have this flag set. The ACK flag, which stands for acknowledgement, is used to acknowledge the successful receipt of a packet. The REST flag, which stands for reset, gets sent from receiver to the sender when a packet is sent to a particular host that was not expecting it. The FIN flag, which stands for finished, means there is no more data from the sender. Therefore, it is used in the last packet sent from the sender. The PSH flag, which stands for push, is somewhat similar to the URG flag and tells the receiver to process these packets as they are received instead of buffering them. The URG flag is used to notify the receiver to process the urgent packets before processing all other packets. So every legitimate TCP connection begins with a TCP three-way handshake, which is used to exchange sequence numbers so that lost packets can be retransmitted and packets can be placed in the proper order. If machine A wants to initiate a connection to machine B, it will start by sending a TCP packet with a SYN control bit set. This packet will include an initial sequence number, which I'll call here ISNA, because it comes from machine A, which is 32 bits long
and typically generated in a pseudo-random fashion by the TCP software on machine A. The ACK number, another 32 bits in the TCP header, is typically set to 0 because it is ignored in this initial SYN. Some operating system variants may make this ACK number non-zero, but either way, it's ignored by the destination machine. So if the destination port is open, that is, there is something listening on that port, it must respond with a SYN ACK packet back, a packet that has both the SYN and ACK control bits set at the same time. This packet will have a sequence number of ISNB, a pseudo-random number assigned by machine B for this connection. The SYN ACK packet will have an acknowledgement number of ISN A plus 1, indicating that machine B has acknowledged the SYN packet from machine A. To complete the three-way handshake, machine A responds with an ACK packet which has a sequence number of ISN A plus 1. It's the next packet, so the sequence number has to change from the value in the original SYN packet. The acknowledgement number field is set to ISNB plus 1, thereby acknowledging the SYN ACK packet, right? So we have now exchanged sequence numbers. All packets going from A to B will have increasing sequence numbers starting at ISN A plus 1, going up by a value of 1 for each byte of data transmitted in the payloads of A to B packets. Likewise, all responses back from B will have sequence numbers starting at ISNB plus 1 and going up for each byte of data from B to A. In essence, we have two streams of sequence numbers in this series of packets, one from A to B, originally based on ISNA, and the other from B to A, originally based on ISNB. Perfect. A TCP segment consists of a segment header and a data section. The TCP header contains 10 mandatory fields and an optional extension field. The optional field is the options field, which is the last field seen on the slide. The TCP header includes a source port and destination port, each 16 bits in length. The source port is the port on the originating machine that emitted the packet. The destination port indicates the port on the target machine the packet should be delivered to. The sequence number and an acknowledgement number allows TCP to track a series of packets to make sure they arrive reliably and pretty much in order. No, absolutely in order. If a packet is lost, TCP will retransmit it. If packets arrive out of order, TCP will adjust them to make sure that they are delivered to the destination services in the proper order. Data offset specifies the size of the TCP header in 32-bit words. The minimum size header is 5 words, and the maximum is 15 words. There is also TCP control bit space, also known as flags, which are incredibly important for tracking the state of a given TCP connection. As you know, we talked about them a few minutes ago. Of course, if you didn't take a break, it was a few minutes ago. But whatever you do, just don't spill on the keyboard. Now, TCP senders use a number called window size, which is in bytes by default, to regulate how much data they send to a receiver before requiring an acknowledgement in return. So if the window size becomes too small, network data transfer will be unnecessarily slow, while if the window size becomes too large, the network link can become saturated or the receiver may not be able to process incoming data quickly enough, also resulting in slow performance. Windowing algorithms built into the protocol dynamically calculate size values and use this field of the TCP headers to coordinate changes between senders and receivers.
TCP traffic. TCP overview. TCP, or Transmission Control Protocol, handles the delivery of packets, including sequencing and errors. You should already have an understanding of how TCP works. We can tell that the port is closed due to the RST ACK packet in red. When analyzing TCP packets, Wireshark can be very helpful and color code the packets in order of danger level. TCP can give useful insight into a network. When analyzing, however, it can also be hard to analyze due to the number of packets it sends. TCP traffic overview. A common thing that you will see when analyzing TCP packets is known as the TCP handshake, which you should already be familiar with. It includes a series of packets. SYN, SYN-ACK, and ACK, that allows devices to establish a connection. Typically, when this handshake is out of order or when it includes other packets like an RST packet, something suspicious or wrong is happening in the network. Scan in the section above is a perfect example of this. TCP packet analysis. We see packet details for a SYN packet. The main thing that we want to look for when looking at a TCP packet is the sequence number and acknowledgement number. Within Wireshark, we can also see the original sequence number by navigating to Edit, Preferences, Protocols, TCP, and Relative Sequence Numbers unchecked boxes. Typically, TCP packets need to be looked at as a whole to tell a story rather than one by one at the detail. This lecture will cover investigating packet-level details by synthesizing the analyst's knowledge and Wireshark functionality for detecting anomalies and odd situations for a given case. Nmap Scans. Nmap is an industry-standard tool for mapping networks, identifying live hosts and discovering the services. As it is one of the most used network scanner tools, a security analyst should identify the network patterns created with it. This section will cover identifying the most common Nmap scan types: TCP Connect Scan, SYN scans, UDP scans. It is essential to know how Nmap scans work to spot scan activity on the network. However, it is impossible to understand the scan details without using the correct filters. We will see the base filters to probe Nmap scan behavior on the network, TCP flags in a nutshell, global search TCP, only SYN flag. SYN flag is set. The rest of the bits are not important. Only ACK flag. ACK flag is set. The rest of the bits are not important. Only SYN, ACK flags. SYN and ACK are set. The rest of the bits are not important. Only RST flag. RST flag is set. The rest of the bits are not important. Only RST ACK flags. RST and ACK are set. The rest of the bits are not important. Only FIN flag. FIN flag is set. The rest of the bits are not important. TCP Connect Scans. TCP Connect Scan in a nutshell relies on the three-way handshake, needs to finish the handshake process. Usually conducted with Nmap, STC command. Usually has a window size larger than 1024 bytes as the request expects some data due to the nature of the protocol. Open TCP port. SYN, SYN ACK, ACK. Open TCP port. SYN, SYN ACK, ACK, RST ACK. Close TCP port. SYN, RST ACK. Open TCP port. Connect. Close TCP port. Connect. The images provide the patterns in isolated traffic. However, it is not always easy to spot the given patterns in big capture files. Therefore, analysts need to use a generic filter to view the initial anomaly patterns, and then it will be easier to focus on a specific traffic point. The given filter shows the TCP Connect Scan patterns in a capture file. SYN scans. TCP SYN scan, in a nutshell, doesn't rely on the three-way handshake. No need to finish the handshake process. Usually conducted with Nmap, SS command. Usually have a size less than or equal to 1024 bytes, as the request is not finished and it doesn't expect to receive data. Open TCP port. SYN. SYN ACK, RST. Close TCP port. SYN, RST ACK. Open TCP port. SYN. Close TCP port. SYN. The given filter shows the TCP SYN scan patterns in a capture file. UDP scans. UDP scan in a nutshell doesn't require a handshake process. No prompt for open ports. ICMP error message for close ports, usually conducted with Nmap SU command. Open UDP port, UDP packet, closed EAD port, UDP packet, ICMP type 3, code 3 message, destination unreachable, port unreachable. UDP ports. The image shows that the closed port returns an ICMP error packet. No further information is provided about the error at first glance. So how can an analyst decide where this error message belongs? The ICMP error message uses the original request as encapsulated data to show the source or reason of the packet. Once you expand the ICMP section in the Packet Details pane, you will see the encapsulated data and the original request is shown in the image. The given filter shows the UDP scan patterns in a capture file.
All right, hello, my friends. So let's get started with today's example. TCP three-way handshake and traffic will be reviewed using Wireshark. Of course, it can be any website that we specify in the web browser. I'm using Chrome, and we will be using oakacademy.de. Now, what are we going to do first? Well, let's get started with putting Wireshark into listening mode. And here's where we start listening. We'll connect to the website, Wireshark Stop Traffic Listening, and we caught 501 packages. Now, when entering the oakacademy.de website, it's got to do the SYN-ACK three-way handshake while TCP makes first connection. Now, let's see if it really did it. Do you think? Let's have a look in the Wireshark traffic. So we need to know the IP address of oakacademy.de first off. The web browser, of course, must have a set DNS. Yeah, sure enough, the DNS is done. See here in the 63rd operation, DNS gets accomplished, and it brings us the IP address of oakacademy.de. Now, it's, of course, very normal for it to do this DNS when logging into the web browser for the very first time. Now, TCP will also follow, so let's go easy with it. We'll go from IP address. So our IP address is 192.168.1.34, oakacademy.de 167.235.52.160. So let's examine the traffic that concerns these two addresses only. Process 63 is DNS. SYN from 65. SYN-ACK from 74. Now at 76, the ACK TCP three-way handshake occurs. All right. Now, here we can also look at the transmission control protocol. Have a look at here. The destination is port 443, so HTTPS. If it was 80, that would, of course, just be HTTP. It's already using the web browser 80 or 443, of course. 80, I just want to reiterate, it's not very safe. It's not hardly used anymore, but you still see it in use. Obviously, HTTPS 443 is preferred. But actually, it doesn't matter if it's our source port. The random number is 58782. Source IP address is 192.168.134 of our computer. And the destination IP address is oakacademy.de's 167.235.52.160. Now, it is important to consider the flags here. SYN flag equals 1. That's the first step, is SYN. And the first step from source to destination on the web to an address on the internet is SYN. I want to be absolutely clear about that. So we'll have a look at the second step, this time source port 443. So we've received data from the web server. oakacademy.de is on our computer, and this time the destination address is 192.168.1.34. And the destination port is, of course, the computer's port of 58782. So the ACK operation has taken place. The web server replied with TCP SYN ACK, right? Now, finally, our computer, which is now the third step of this three-way handshake, the user's computer, 192.168.1.34, destination, oakacademy.de, IP address of 167.235.52.160, sends ACK acknowledgement, right, to port 443. So that means in the last step, the ACK goes from our computer to the web server, and this creates that three-way handshake. The second step, the server acknowledges with ACK. In the third step, the user acknowledged with ACK. And now they will stream data back and forth because the TCP three-way handshake is now complete. In fact, we can actually see this represented graphically. So when we choose statistics flow graph, we see the flow with arrows. Now let's choose limit to display filter, and DNS appears before the TCP3 handshake. And three-way is done. You can see that with the arrows. We'll enlarge it here with a zoom in using the plus key. And well, let's just say TCP here. And let's say the stream type is TCP. All right, so that looks a little better. So here we can see the SYN gets started, 192.168.1.34. And if we look at the direction of the arrow, oakacademy.de sends a SYN to the IP address 167.235.52.160. And immediately after, it replies with ACK from 443 HTTPS port and says, yeah, hey, that's okay. Pretty cool. And in the last step, the source is our computer, 192.168.1.34, and it sends a last agreement message with ACK. So they complete their three-way handshake. And here, the traffic actually gets shown very clearly with arrows. All right, so that's it for that example, my friends. I'll see you next time. A full duplex communication is established. UDP is another protocol of transport layer, layer 4, used primarily for establishing low latency and loss tolerating connections between applications on the internet. TCP has emerged as the dominant protocol used for the bulk of internet connectivity, owing to its services for breaking large data sets into individual packets, checking for and resending lost packets, and reassembling packets into the correct sequence. But these additional services come at a cost in terms of additional data overhead and delays called latency. In contrast, UDP just sends the packets, which means that it has a much lower bandwidth overhead and latency. But packets can be lost or received out of order as a result, owing to the different paths individual packets traverse between sender and receiver. So UDP uses a simple connectionless communication model with a minimum of protocol mechanism. It has no handshaking dialogues and thus exposes the user's program to any unreliability of the underlying network. There is no guarantee of delivery, ordering, or duplicate protection. UDP is suitable for purposes where error checking and correction are either not necessary or are performed in the application. UDP is an ideal protocol for network applications in which perceived latency is critical, such as gaming, voice, and video communications, which can suffer some data loss without adversely affecting perceived quality. In addition, since it's transaction-oriented, suitable for simple query response protocols such as the domain name system or the network time protocol. The UDP header is pretty simple. It consists of 4 fields, each of which is 2 bytes, 16 bits. The use of the fields checksum and source port is optional in IPv4. Are you surprised to hear that the source port is optional? But don't be, because, as you know, a UDP packet does not expect to get a reply in general. And again, since UDP doesn't care about the errors, the checksum field is, again, optional. Source port identifies the sender's port, and the destination port identifies the receiver's port as well. And the length field specifies the length of the UDP header and data in bytes. So now's a good time to compare the two protocols, UDP and TCP, as a brief summary. Most services on the internet use either TCP or UDP, which are carried end-to-end across the network using IP, either IPv4 or IPv6. The Transmission Control Protocol, TCP, and User Datagram Protocol, UDP, are very different. TCP is a connection-oriented protocol which tries to ensure reliable, in-order delivery of packets. If packets are lost, TCP automatically retransmits them. If they arrive out of order, TCP will resequence them before handing them up to an application. UDP is connectionless. The UDP software makes no attempt to associate streams of packets together. So as far as UDP is concerned, each packet is completely independent, unrelated to other packets. No attempt is made by UDP for retransmission or resequencing. If a packet is lost via UDP, it's up to the higher layer application to resend it. Well, howdy, friends. So we've got an example here for you. We're going to examine the operation of the Tracert command. So the Tracert command, the target can be a web server or a computer. So it's basically a command to detect how many routers it has passed through and how much time has taken to get through that route. It can run on Linux or Windows. But in Windows, the command is executed by writing Tracert, not Traceroute. So we're going to use the Wireshark traffic monitoring program to monitor and analyze traffic. So in fact, we're going to start with Tracert, Google's DNS server. Of course, we're going to start up Wireshark first so that we can listen. So add the command prompt type Tracert 8.8.8.8 and press enter. Now, let's count how many routers does it go through. Looks like 3. All right, so when that's done, you can see Google DNS is reserved. We can stop it now. So we tracered the Google DNS server from the 8.8.8.8 IP address. In order to reach the Google DNS server, it passed through 10 routers, and the 11th reached the Google DNS server. So let's analyze this traffic that we listen to in Wireshark. Of course, we will have to filter it. It's actually probably the most logical way to use the 8.8.8.8 Tracert address while filtering. So let's just filter by typing ip.host equals 8.8.8.8. All right, so in total, 132 packages were caught. We filtered out the ones that interest us. And see, Traceroute actually does a trick and kind of does a hacking operation, but how's it doing it? It causes time to be exceeded by increasing the TTL values from 1, and then it detects all routers one by one. So if you look in here, there are 3 attempts. 1, 2, 3, always attempted 3 times. But here's the thing. And the TTL found the last 8.8.8.8. It increased until the 11th. After the 11th, the TTL did not increase. So at 11, Google DNS found the server. No need to go any further. Traceroute finds routers between the IP addresses we query and our IP address. So it's actually found them all, and while doing so, it does it step by step by playing with that time to live, the TTL, increasing it by 1 each time. So let's dig in a little deeper. So Traceroute attempts 3 times, and on each router, it tries 3 times on each what we call a hop. So now let's look at the traffic from the beginning. Our IP address is 192.168.1.34. Of course, this is our private IP address on the local internal network. And it's already seen here in gateway routing. So we will need to review on Wireshark from the private IP address that we use. See, if we examine it from the beginning, it made TTL equals 1, tried 3 times. Timeout message gets returned. Then it ups it to 2, TTL equals 2, and return from which IP address the router replied. We can also look at the addresses that send back timeout messages, and we'll compare that with the terminal screen. So 192.168.1.1 first returned from our gateway, obviously. Then it returns from 100.98.128.1. Then it returns from 81.212.73.9. See, TTL equals 3 in the 3rd stage. And in the 4th stage, returns from 81.212.242.8, TTL equals 4. Now, there is an asterisk here. The router firewall with this asterisk cannot receive a response. That is, it cannot resolve it. If we see such starry statements, you can think of them as if we didn't get the firewall's response back from there. Okay, so we have to think like we didn't get an answer. Let's go to the last one, the 10th. So the 10th TTL, this is the time to live. And let's go to the answer. The source IP address we get here is 142.251.246.233. It's also getting a response back from a router there. Rotation times are also 50 milliseconds, 50 milliseconds, and 51 milliseconds. Now, like we were saying, it reaches Google's DNS server in the 11th step. And look at the TTL equals 11. 8.8.8.8 IP addresses. Okay, now it found me. Traceroute query's over. So there's nowhere else to go anymore, basically. So here we find the endpoint, the final point. The TTL values are actually the important point to note here, right? Because resolution is done with TTL and time exceeded messages. Now, You also might hear about terms like hacking, but this is how it performs the analysis. So when we analyze the traffic in graphic form, it's going to be a whole lot easier to see with the arrows when you show it with directions that it's flowing. And coincidentally, we do it with the flow graph from statistics. So if you limit to display filter, it can fit the graphics to the screen. But look where it starts. Our Tracert residence 8.8.8.8 was questioned. So we get a response from the gateway router, our own modem, right? So we tried there 3 times. And the number of attempts is always going to be 3. There are also 3 time exceeded messages. The return response is colored green on the graph, and the pink background colors are the ones that we sent. And for those with the black background, the time's been exceeded. And respectively, traffic with all router IP addresses is now shown with arrows. Now it's necessary to minimize the screen to see the last IP address. Let's see Google DNS server in the graph. Yeah, so it finds it in step 11 after router with the IP address of 142.251.246.233. So this is the last router in between after that. There's no router left. And the 11th, the time to live, the TTL equals 11. We reach 8.8.8.8, the IP Google DNS server. And this is what the arrows show, right? The number of hops, the number of attempts that can be counted here on the chart. So 3 attempts are standard, but of course the number of hops can vary. As a result, 3 attempts were made, yeah. So the time intervals are relatively close to each other, 50 milliseconds, 51 milliseconds, 51 milliseconds, Traceroute. So I'll remind you again, Tracert echo request and reply in time exceeded format in Windows. With ICMP, Tracert runs on Windows. On Linux, UDP packets can also be used for request TTL. Now, it is actually written into the Linux terminal in Traceroute format. Since our computer is Windows operating system, hey, round trips have been seen with your ICMP packages. All right, cool. So, hey, that's it for right now.
Dynamic Host Configuration Protocol, HCP traffic, DHCP analysis, DHCP protocol, or Dynamic Host Configuration Protocol, is the technology responsible for managing automatic IP address and required communication parameters assignment. DHCP investigation in a nutshell. Notes: Wireshark filter, global search, DHCP or boot P. Filtering the proper DHCP packet options is vital to finding an event of interest. DHCP request packets contain the hostname information. DHCP ACK packets represent the accepted requests. DHCP NACK packets represent denied requests. Due to the nature of the protocol, only option 53 request type has predefined static values. You should filter the packet type first, and then you can filter the rest of the options by applying as column or use the advanced filters like contains and matches. Request 3, ACK 5, NACK 6. DHCP request options: hostname, requested IP address, requested IP lease time, client's MAC address. Hostname contains keyword. DHCP ACK options: domain name, assigned IP lease time. Domain name contains keyword. DHCP NACK options: message ejection details, reason. As the message could be unique according to the case, situation, it is suggested to read the message instead of filtering it. Thus, the analyst could create a more reliable hypothesis. Result by understanding the event circumstance. DHCP, identifying host. When investigating a compromise or malware infection activity, a security analyst should know how to identify the hosts on the network apart from IP to MAC address match. One of the best methods is identifying the hosts and users on the network to decide the investigation's starting point, and list the hosts and users associated with the malicious traffic activity. Usually, enterprise networks use a predefined pattern to name users and hosts. While this makes knowing and following the inventory easier, it has good and bad sides. The good side is that it will be easy to identify a user or host by looking at the name. The bad side is that it will be easy to clone that pattern and live in the enterprise network for adversaries. There are multiple solutions to avoid these kinds of activities, but for a security analyst, it is still essential to have host and user identification skills.
Oh, hello, my friends. So in this example, we're going to make the DHCP server application. We're going to be able to see the DHCP in 4 stages that we talk about by doing DHCP filtering on the traffic that we capture in Wireshark. And what are they again? Discovery, offer, request, act. And we're going to examine these 4 stages in detail. So where do we start? Well, how about with discovery? So what is it that we are discovering? Basically, we're discovering the DHCP server located on the network. Who is discovering, though? Currently 0.0.0.0 without any ID. So nothing, nobody. Now, already in the search for IP identity, of course, how do we go and get the identity from the state? Well, same here on the DHCP server. We need to get our IP number. But first, we will need to find that DHCP server. So that's what Discover does. This message is broadcast to all the devices on a network to find the DHCP server. Source MAC address 02EC21B09CFD. Destination MAC address. We got the quad F. Source IP address 0.0.0.0 and destination IP 255.255.255.255. Oh, one more thing. UDP protocol is being used. So what's going to happen next? Now, the second stage is offer. So the DHCP server on network 10.10.0.1. The DHCP server basically says, hey, yo, I'm here. It says, I can give you an IP address. And it offers an IP address. So in this proposal, the source IP address is 10.10.0.1. The destination IP address is 10.10.169.48. The source MAC address, the DHCP server, is 02C8855B55AAA. The destination MAC address is 02EC21B09CFD. So here, the offer message is unicast by the DHCP server. The DHCP server provided a lease time of an hour, 3,600 seconds for the offered IP address, 10.10.169.48. Third request, well, still no IP address. Destination IP 255.255.255.255. So it's broadcasting from the DHCP server. Hey, you know what? I'll accept this IP address, 10.10.169.48. It's okay. So it tells the DHCP server that it's going to accept the 3,600 second lease time that it's offering. So when a client receives an offer message, the DHCP request message responds with a broadcast. A message indicating that the IP address has been accepted is broadcast to the server, and that completes the broadcast. The fourth and final stage is ACK. So here's where they shake hands. Now, it's accepted, right? Another thing to note here is port addresses, the port numbers, 67 and 68. So 67 and 68 are DHCP port addresses. All right, so everything is acknowledged, everything is accepted. Now the server is going to make a login to the client's computer with the provided IP address and lease time. So this IP address will not be provided by the server to another computer. Okay, the destination MAC address is 02EC21B09CFD, and the destination IP address is 10.10.169.48, and the source IP address is 10.10.0.1. And the source MAC address is 02C85B55AAA. That's the server MAC address, and the lease time, of course, 3,600 seconds. So before this period expires, a retrigger, a request must be made. And this period must be extended by the computer that receives this IP address. So what's this time extension? Its number could be given to another computer. See, and then failure to extend this period means that computer is going to be shut down, right? So the client computer needs to retrigger. So how can we see this flowing traffic in graphic form? Statistics flow graph, you can see in front of you, and we can see it very clearly now. So first of all, our computer without an IP address broadcasts, so it's doing discovery. Then our 10.10.0.1 server makes an offer, and an IP address is now being offered. So this 10.10.169.48 is making an offer to the client. Will it accept? The client accepts, says OK, sending a request, and broadcasting again. And then in the final stage, the computer that's received the IP identification number and the address of 10.10.0.1 and 10.10.169.48 handshake, the acknowledgement, or the ACK. And here is the graphical representation of the traffic. All right, my friends, we're done with that example. The often used analogy to explain the domain name system is that it serves as the phone book for the internet by translating human-friendly computer host names into IP addresses. Simply, DNS is a directory of names that match with IP addresses. As you may know, each device connected to the internet has a unique IP address which other machines use to find the device. DNS servers eliminate the need for humans to memorize IP addresses, such as 212.80.75.134. Think about the websites you visit every day, Google and YouTube, Facebook, Twitter, etc. Without DNS, we would have to reach these sites by using their IP addresses instead of their names. I think remembering the names is so much easier than remembering the strange numbers. But it's still possible to reach the computer with that strange number string as well. Now, DNS deserves to have far more time spent on it. It could be a whole course in and of itself. But I just want to explain it simply without going too deep. So when you enter the URL, such as www.google.com, into the web browser, the request is not directly sent to the Google servers. Instead, the request goes to the DNS server that uses a lookup table to determine the IP address of the website that is being requested. Then it forwards this information to the proper servers and returns the information requested to your specific browser. DNS server is a computer server which contains a database of public IP addresses and their associated host names. It translates those common names to IP addresses as requested. DNS servers run special software and communicate with each other using special protocols. DNS is a client-server network communication system. DNS clients send their requests to and receive the responses from DNS servers. The requests containing the name and resulting in an IP address being returned from the server are called forward DNS lookups. The requests containing IP addresses and resulting in the names are called the reverse DNS lookups. The DNS directory that matches name to number isn't located all in one place. Pretty much like the internet itself, the directory is distributed around the world, stored on domain name servers that all communicate with each other on a very regular basis to provide updates as well as redundancies. With more than 332 million domain names listed by the end of 2017, a single directory would be very large indeed. So when you type mail.google.com into your browser sends a query over the internet to find the website. It's a query seeking to match the domain name with its corresponding IP address. So let's follow the path of this question over the internet infrastructure. The first server your query interacts with is the DNS resolver, which can be operated by your ISP, Internet Service Provider. A resolver is basically responsible for initiating and sequencing the queries that ultimately lead to a full resolution. Domain name resolvers determine the domain name servers responsible for the domain name in question by a sequence of queries, starting with the rightmost, in other words, top-level domain label. Assuming the resolver has no cached records to accelerate the process, which is the worst-case scenario, the resolution process starts with a query to one of the root servers. The root servers are running all over the world, and each one knows DNS information about top-level domains, or TLD, such as .com. So to begin answering your query, The resolver asks a root server for DNS information about .com. So there are 13 sets of root servers in more than 300 locations around the world. Each TLD DNS name server stores the address information for second-level domains within the top-level domain, .com in our example. The second-level domain is google.com. When your query reaches the TLD server answers with the IP address of the domain's name server, which will provide the next piece of the puzzle. So this is the final step of address resolution. The recursive resolver sends the query to the domain's name server. This DNS server knows the IP address for the full domain, mail.google.com, and that answer is returned to the recursive resolver. Now that the recursive resolver knows the IP address for the domain name in your query, the recursive resolver tells the browser what the IP address is. So finally, your browser can send a request to the website to retrieve the website's content using the IP address it just learned. This whole process might seem, well, complicated. It certainly sounds it to talk it out, but really takes very little time at all.
Tunneling traffic, ICMP and DNS. Traffic tunneling is also known as port forwarding, transferring the data, resources in a secure method to network segments and zone. It can be used for internet to private networks and private networks to internet flow, direction. There is an encapsulation process to hide the data, so the transferred data appear natural for the case, but it contains private data packets and transfers them to the final destination securely. Tunneling provides anonymity and traffic security. Therefore, it is highly used by enterprise networks. However, as it gives a significant level of data encryption, attackers use tunneling to bypass security perimeters using the standard and trusted protocols used in everyday traffic like ICMP and DNS. Therefore, for a security analyst, it is crucial to have the ability to spot ICMP and DNS anomalies. ICMP analysis, Internet Control Message Protocol. ICMP is designed for diagnosing and reporting network communication issues. It is highly used in error reporting and testing. As it is a trusted network layer protocol, sometimes it is used for denial of service attacks. Also, adversaries use it in data exfiltration and C2 tunneling activities. ICMP analysis in a nutshell. Usually, ICMP tunneling attacks are anomalies appearing, starting after a malware execution or vulnerability exploitation. As the ICMP packets can transfer an additional data payload, adversaries use this section to exfiltrate data and establish a C2 connection. It could be a TCP, HTTP, or SSH data, as the ICMP protocols provide a great opportunity to carry extra data. It also has disadvantages. Most enterprise networks block custom packets or require administrator privileges to create custom ICMP packets. A large volume of ICMP traffic or anomalous packet sizes are indicators of ICMP tunneling. Still, the adversaries could create custom packets that match the regular ICMP packet size, 64 bytes. So it is still cumbersome to detect these tunneling activities. However, a security analyst should know the normal and the abnormal to spot the possible anomaly and escalate it for further analysis. Global search ICMP, ICMP options, packet length, ICMP destination addresses, encapsulated protocol signs in ICMP payload. DNS analysis. Domain name system is designed to convert IP domain addresses to IP addresses. It is also known as a phone book of the internet. As it is the essential part of web services, it is commonly used and trusted and therefore often ignored. Due to that, adversaries use it in data exfiltration and C2 activity. DNS analysis in a nutshell. Similar to ICMP tunnels, DNS attacks are anomalies appearing starting after a malware execution or vulnerability exploitation. Adversary creates or already has a domain address and configures it as a C2 channel. The malware or the commands executed after exploitation sends DNS queries to the C2 server. However, these queries are longer than default DNS queries and crafted for subdomain addresses. Unfortunately, these subdomain addresses are not actual addresses. When this query is routed to the C2 server, the server sends the actual malicious commands to the host. As the DNS queries are a natural part of the networking activity, these packets have the chance of not being detected by network perimeters. A security analyst should know how to investigate the DNS packet links and target addresses to spot these anomalies. Global search, DNS. DNS options, query length. Anomalous and non-regular names in DNS addresses. Long DNS addresses with encoded subdomain addresses. Statistical analysis like the anomalous volume of DNS requests for a particular target. Detecting suspicious activities in chunked files is easy and a great way to learn how to focus on the detail. DNS traffic. DNS overview. DNS, or Domain Name Service Protocol, is used to resolve names with IP addresses. Just like the other protocols, you should be familiar with DNS. There are a couple of things outlined below that you should keep in the back of your mind when analyzing DNS packet. Query response, DNS servers only. UDP, if any one of these is out of place, then the packets should be looked at further and should be considered suspicious. We can see a packet capture with multiple DNS queries and responses. Instantly looking at the packets, we can see what they are querying. This can be useful when you have many packets and need to identify suspicious or unusual traffic quickly. DNS traffic overview, DNS query. Looking at the below query, we really have two bits of information that we can use to analyze the packet. The first bit of information we can look at is where the query is originating from. In this case, it is UDP 53, which means that this packet passes that check. If it was TCP 53, then it should be considered suspicious traffic and needs to analyzed further. We can also look at what it is querying as well. This can be useful with other information to build a story of what happened. When analyzing DNS packets, you really need to understand your environment and whether or not the traffic would be considered normal within your environment. DNS response. Below we see a response packet. It is similar to the query packet, but it includes an answer as well, which can be used to verify the query.
All right. Hello, my friends. Thanks for coming back. So we're going to do an example now on DNS query. We first have to start up Wireshark traffic listening and put it into listening mode, of course. So we run the web browser Chrome to connect to oakacademy.de. So we're going to stop Wireshark and let's do a DNS filter here. Now, how many packets come in when we do Wireshark DNS? 33. All right, so let's engage a more special filter here. Let's do dns.query.name equals oakacademy.de. Right, so you see how that just focuses it, and it resolves the internet traffic system that works by connecting the DNS domain name to the IP address. DNS allows the web browser to find directions by its IP address. That is, it asks the DNS server for the IP address of the domain name that we wrote in the browser. Okay. Now, the query system that brings the IP address of the domain name to the web browser is called DNS, Domain Name Services. So you see, Wireshark oakacademy.de asks the DNS server for the IP address from 192.168.1.1. And in response, the IP address value is 167.235.52.160. DNS query 180 number operation A IPv4 query gets made. All right. HTTPS query was made in 179. Response comes in transaction number 187. The IP type is version 4. 4 octet IP is requested. DNS query is made from 192.168.1.1. Port 53 is always the DNS query port. Did you say it with me? Of course, service port 53 works for DNS, and DNS query occurs as a UDP packet. So DNS query gets made from our IP address 192.168.1.34 to DNS server 192.168.1.1 IP address. All right. The source port of the server is 53. Now, our port is not very important, is it? You could use a random port, 63525. This 53 is important, right? 53 DNS, and a DNS request is made by UDP. Now, in response, an IP address 167.235.52.160 gets sent. So what do you say? Can we connect to the website using this IP address, 167.235.52.160? Well, yeah, so when you type it into the web browser, it connects to the oakacademy.de website. See, DNS already does that. So in other words, the whole internet is guided all over the world by numbers and IP addresses. DNS finds that and brings you to the IP address. Now let's say again that there is DNS UDP protocol here, UDP content, oakacademy.de. And let's look at the flow with the statistics flow graph option. And there was a DNS query from 192.168.1.34. DNS query from 192.168.1.1 occurs. Now your internet service provider's DNS server answers the standard A-type IPv4 query, right, from oakacademy.de port 53. So the reply is IPv4 address 167.235.52.160, and the reply is sent by the DNS server. Now you could also enter a web browser with 167.235.52.160's IP address, or with the domain name oakacademy.de. You see how, in the end, it's the same outcome. All right, my friends, so that wraps up this example. I want to take you through something else next time, so stick around.
Hypertext Transfer Protocol, HTTP, is an application protocol. Hypertext is basically structured text that uses logical links between nodes containing text. And HTTP is the protocol to exchange or transfer hypertext. So HTTP is a stateless protocol. That means no information is retained by either sender or receiver. It functions as a request-response protocol in the client-server computing model. A web browser, for example, may be the client, and an application running on a computer that's hosting a website may be the server. The client submits an HTTP request message to the server. The server, which provides resources such as HTML files and other content, returns a message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So the most used HTTP request is GET. A GET request is designed to request server resources. With this type of request, the parameters are sent to the server inside the URL. A POST request is designed to request server resources as well as a GET request. Unlike a GET request, parameters are sent to the server inside the body of the request instead of the URL. Well, it's still possible to send the parameters inside the URL, but if you use a POST request, it's better to send parameters inside the body than inside the URL. So what's the advantage of sending parameters inside the body instead of the URL? Almost always, the traffic between the server and the client is logged on the server side. Such log files usually contain the URL. If you send the parameters in the URL, they are saved as clear text in your log files. So anyone who can see the log files can also see your sensitive parameters. You should use POST requests to send sensitive data. But please note that it's not enough for the privacy of the traffic, because any man in the middle who listens to the network will see the parameters even though they are inside the body of the request message. So you should encrypt your traffic, always. Now the server, which provides resources such as HTML files and other content, returns a response message to the client. The response contains completion status information about the request and may also contain requested content in its message body. So every response has a 3-digit response status code, such as 200 OK, 302 found, etc. HTTP traffic. HTTP, or Hypertext Transfer Protocol, is a commonly used port for the World Wide Web and used by some websites. However, its encrypted counterpart, HTTPS, is more common, which we will discuss in the next. HTTP is used to send GET and POST requests to a web server in order to receive things like web pages. Knowing how to analyze HTTP can be helpful to quickly spot things like SQLi, web shells, and other web-related attack vectors. HTTP traffic overview. You should already have a general understanding of how HTTP works before completing this lecture. HTTP is one of the most straightforward protocols for packet analysis The protocol is straight to the point. We can see a sample HTTP packet. Looking at an HTTP packet, we can easily gather information since the data stream is not encrypted like the HTTP counterpart, HTTPS. Some of the important information we can gather from the packet is the request URI, file, data, and server. Now that we understand the basic structure of an HTTP packet, we can move on to looking at a sample HTTP packet capture to get hands-on with the packets. Practical HTTP packet analysis. To get an understanding of the flow of HTTP packets and get hands-on with the packets, we analyze the http.cap file. After opening the PCAP, we can see that this is just a simple HTTP packet capture with a few requests. Navigating deeper into the packet capture, we can look at the details of one of the HTTP requests. From this packet, we can identify some very important information like the host, user agent, requested URI, and response. We can use some of Wireshark's built-in features to help digest all of this data and organize it for further future analysis. We can begin by looking at a very useful feature in Wireshark to organize the protocols present in a Capture the Protocol hierarchy. Navigate to Statistics Protocol Hierarchy. This information can be very useful in practical applications like threat hunting to identify discrepancies in packet captures. The next feature in Wireshark we will look at is the Export HTTP object. This feature will allow us to organize all requested URI in the capture. To use Export HTTP object, navigate to File, Export Objects, HTTP. Similar to the protocol hierarchy, this can be useful to quickly identify possible discrepancies in capture. The last feature we will cover in this section of this lecture is endpoints. This feature allows the user to organize all endpoints and IPs found within a specific capture. Just like the other features, this can be useful to identify where a discrepancy is originating from. To use the endpoints feature, navigate to Statistics Endpoint. HTTP is not a common protocol to see too much as HTTPS is now more commonly used. However, HTTP is still used often and can be very easy to analyze if given the opportunity. HTTP analysis. Hypertext Transfer Protocol HTTP is a clear text-based request response and client-server protocol. It is the standard type of network activity to request serve web pages, and by default, it is not blocked by any network perimeter. As a result of being unencrypted in the backbone of web traffic, HTTP is one of the must-to-know protocols in traffic analysis. Following attacks could be detected with the help of HTTP analysis: phishing pages, web attacks, data exfiltration, command and control traffic C2, HTTP analysis in a nutshell. HTTP2 is a revision of the HTTP protocol for better performance and security. It supports binary data transfer and request once multiplexing. HTTP request methods: GET, POST, REQUEST, listing all requests. HTTP response status codes: 200 OK, request successful, 401 unauthorized, URL needs authorization, 403 forbidden, no access to the requested URL, 404 not found, server can't find the requested URL, 405 method not allowed, use method is not suitable or blocked, 503 service unavailable, request not completed server, or service is down. HTTP parameters: user agent, browser and operating system identification to a web server application. Request URI points the requested resource from the server. HTTP parameters: server name, host name of the server. Connection, see connection status. Line-based text data, clear text data provided by the server. HTML form URL encoded, web form information. User agent analysis. As the adversaries use sophisticated techniques to accomplish attacks, they try to leave traces similar to natural traffic through the known and trusted protocols. For a security analyst, it is important to spot the anomaly signs on the bits and pieces of the packet. The user agent field is one of the great resources for spotting anomalies in HTTP traffic. In some cases, adversaries successfully modify the user agent data, which could look supernatural. A security analyst cannot rely only on the user agent field to spot an anomaly. Never whitelist a user agent, even if it looks natural. User agent-based anomaly, threat detection. Hunting is an additional data source to check and is useful when there is an obvious anomaly, If you are unsure about a value, you can conduct a web search to validate your findings with the default and normal user agent info. User agent analysis in a nutshell. Global search, http.useragent, research outcomes, different user agents, information from the same host in a short time notice. Non-standard and custom user agent info. Subtle spelling differences. Mozilla is not the same as Mozilla or Mozilla. Audit tools info like Nmap and SQL map in the user agent field. Payload data in the user agent field.
All right, hello, my friends. Our example for this one is the HTTP, the protocol formerly known as Hypertext Transfer Protocol. So we're going to use this HTTP as a protocol in our example website that operates only on HTTP. Right here, http://hobielectronic.org/. So why don't we run it, and we'll capture and analyze this traffic in Wireshark. So we're listening with Wireshark, and you start it up, and then go to the website, http://hobielectronic.org. All right, so let's have a look at the Space Shuttle HTML image, my first paragraph text on the web page. And we'll stop listening with Wireshark. Now we can make an HTTP filter. 4 HTTP packets were filtered out of 253 in the registered traffic. So the IP address of the site, hobielectronic.org, just happens to be 45.151.251.32. And our own computer's IP address, 192.168.1.34. All right, so 4 already processed HTTP in traffic here. And operations 29, 31, 51, and 125. So we'll first have a look at the web browser on our computer. It makes a Chrome GET request. And from whom would that be? From the IP address 45.151.251.32. That is from the website, hobielectronic.org. Right? So this is the response that comes with this status code 200. Now, status code number 200 says, hey, everything's A-OK. Let's proceed. So, okay, let's do it. Indicates that all is well. Data flow has been successfully completed. But you pretty much need to remember these status codes, my friends, all right? Whether it's HTTP or using other different protocols, status codes are pretty important when transacting on the web. You got to remember what they all mean. So let's have a look at the answer again in the line-based text data section. So the content is already text HTML, and the contents of the index.html file are going to be the same. So what is it here? Space Shuttle, an HTML image, and my first paragraph. Okay, so that's all the same. And we said HTTP insecure, and we can see that here too. So you save all this and upload it to the server's index.html. Upload the image file to the same folder, and it works just the same. There's obviously no difficulty. And this data flow takes place over the HTTP port 80 on the web server. All right. Now, let's have a look in process 51. The image file is requested with GET. The content of the space14.jpg file is received from the web server in process number 125. All right, so in the JPEG file interchange format line, the image file content can be viewed in hexadecimal format. Export packet byte selection shows the file name and path and saves these hexadecimal codes as an image file on our computer. So now let's save it as logo.jpg on the desktop. And look at this, we just downloaded the picture, right? So that's how insecure HTTP is, right? So let's have a look at the flow of traffic from the flow option, my friends. So from HTTP stream option, red section, get request made by our computer and Chrome browser, request from hobielectronic.org, connection type keeps alive, and agent Windows operating system, browser Chrome, languages used, history. Now you see the blue part. This is the response content of the server, HTTP version 1.1. So 200 is our status code saying successful. All right. Content, text, date, data length. But the important thing here is the main homepage on the server that comes with this response. The body content of the index.htm page we referred to. All right, same as Space Shuttle, HTML image and my first paragraph within the body. All right, so it says file type is HTML. Now 51 and 125 are the get, request, and responses of the JPEG image file. Red part is a request, blue part is a response. With get, the space14.jpg file is requested from the HTTP hobbyelectronic.org web server. So response sent the content of space14.jpg in ASCII hexadecimal code, image, JPEG format, right? So when we save these codes, we can actually see the image content. We cannot get a result just by looking at the hexadecimal codes. We wouldn't be able to understand the pixel content from the codes. So get request. We made a request to the website hobbyelectronic.org. Since the values are such a connection type, agent type, date, etc., are text, we can immediately understand it, right? So status code 200 is successful. HTML content, HTML codes in the body are still understandable. Then the image file request in the server's 200 status code can be understood as a successful response. But the image file content is not text, but we can still record and view them. So when we have a look at the flow in its graph form, statistics, flow graph option, get request made here, to whom? To the server, 45.151.251.32, 192.168.1.34 is making this request, writes a response to the computer. Now there are also comments here, 200, okay, status code. And the text, HTML content arrows, let us see the traffic going back and forth visually, and we see the IP addresses here. No names, only numbers. IP addresses and port numbers are used here, and we see them quite clearly. And there is the traffic that's indicated by the 4 arrows. First of all, the text content was requested with GET. The web server responded and said, yep, A-OK. That's number 200. And the image, space14.jpg, was requested with GET. Now, the web server responded, sent a JPEG image, and said 200, A-OK. Now, look, even the name of the file gets written. See, that's all HTTP, right? Everything is clear. Text, image, everything for copy and download and usage. So we've got IP addresses and port numbers. So let's have a look at AD is always HTTP. And by the way, HTTP is always port 80 on the server. But guess what? That wraps up our example here.
Now, HTTPS consists of communication over HTTP within a connection encrypted by TLS, Transport Layer Security, or its predecessor, SSL, the Secure Sockets Layer. The main motivation for HTTPS is authentication of the visited website and protection of the privacy and integrity of the exchanged data. So let's see how a typical encrypted connection between the server and the client is established. The client sends the information that the server needs to communicate with the client using SSL. This information contains the client's SSL version number, cipher settings, and session-specific data. The server then sends the information that the client needs to communicate with the server over SSL. The server also sends its own certificate. The client uses the information sent by the server to authenticate the server. So using all data generated in the handshake thus far, the client creates the pre-master secret for the session, encrypts it with the server's public key, and then sends the encrypted pre-master secret to the server. The server uses its private key to decrypt the pre-master secret, and both the client and the server perform a series of steps to generate the master secret. Then, they use the master secret to generate the session keys, which are symmetric keys used to encrypt and decrypt information exchanged during the SSL session and to verify its integrity. The client sends a separate message indicating that the client portion of the handshake is finished, and the server sends a separate message indicating that the server portion of the handshake is finished. HTTP's traffic. HTTPC, or Hypertext Transfer Protocol Secure, can be one of the most annoying protocols to understand from a packet analysis perspective and can be confusing to understand the steps needed to take in order to analyze HTTPS packets. HTTPS traffic overview. Before sending encrypted information, the client and server need to agree upon various steps in order to make a secure tunnel. 1. Client and server agree on a protocol version. 2. Client and server select a cryptographic algorithm. 3. The client and server can authenticate to each other. This step is optional. 4. Creates a secure tunnel with a public key. We can begin analyzing HTTPS traffic by looking at packets for the handshake between the client and the server. Client hello packet showing the SSL record layer, handshake type, and SSL version. The server hello packet sending similar information as the client. Hello packet, however, this time it includes session details and SSL certificate information. The client key exchange packet. This part of the handshake will determine the public key to use to encrypt further messages between the client and server. In the next packet, the server will confirm the public key and create the secure tunnel. All traffic after this point will be encrypted based on the agreed-upon specifications listed above. The traffic between the client and the server is now encrypted, and you will need the secret key in order to decrypt the data stream being sent between the two hosts. Practical HTTPS packet analysis. In order to practice and get hands-on with HTTPS packets, we can analyze the Snake Oil 2 PCAP and decryption key. We first need to load the PCAP into Wireshark. Navigate to File, open and select the Snake Oil 2 PCAP. From looking at the above packet capture, we can see that all of the requests are encrypted. Looking closer at the packets, we can see the HTTPS handshake as well as the encrypted requests themselves. Let's take a closer look at one of the encrypted requests. We can confirm from the packet details that the application data is encrypted. You can use an RSA key in Wireshark in order to view the data unencrypted. In order to load an RSA key, navigate to Edit, Preferences, Protocols, TLS. If you are using an older version of Wireshark, then this will be SSL instead of TLS. You will need to fill in the various sections on the menu with the following preferences. IP address 127.0.1 port. Protocol HTTP key file. RSA key location. Now that we have an RSA key imported into Wireshark, if we go back to the packet capture, we can see that the data stream is now unencrypted. We can now see the HTTP requests and unencrypted data streams. Looking further at one of the details of the packet, we can see the unencrypted data stream closer. Looking at the packet details, we can see some very important information, such as the request URI and the user agent, which can be very useful in practical applications of Wireshark, such as threat hunting and network administration. We can now use other features in order to organize the data stream, like using the Export HTTP Object feature. To access this feature, navigate to File, Export Objects, HTTP. Decrypting HTTPS traffic. When investigating web traffic, analysts often run across encrypted traffic. This is caused by using the Hypertext Transfer Protocol Secure HTTPS protocol for enhanced security against spoofing, sniffing, and intercepting attacks. HTTPS uses TLS protocol to encrypt communications, so it is impossible to decrypt the traffic and view the transferred data without having the decryption key pairs. As this protocol provides a good level of security for transmitting sensitive data, attackers and malicious websites also use HTTPS. Therefore, a security analyst should know how to use key files to decrypt encrypted traffic and investigate the traffic activity. The packets will appear in different colors as the HTTP traffic is encrypted. Also, protocol and info details, actual URL address, and data returned from the server will not be fully visible. HTTPS parameters request, listing all requests, HTTP request, TLS, global TLS search, TLS client request, TLS server response, local simple service discovery protocol, SSDP. Similar to the TCP three-way handshake process, the TLS protocol has its handshake process. The first two steps contain client hello and server hello messages. The given filters show the initial hello packets in a capture file. These filters are helpful to spot which IP addresses are involved in the TLS handshake. An encryption keylog file is a text file that contains unique key pairs to decrypt the encrypted traffic session. These key pairs are automatically created per session when a connection is established with an SSLA/TLS-enabled web page. As these processes are all accomplished in the browser, you need to configure your system and use a suitable browser to save these values as a keylog file. Chrome and Firefox support this. To do this, you will need to set up an environment variable and create the SLK log file, and the browser will dump the keys to this file as you browse the web. SSL, TLS key pairs are created per session at the connection time, so it is important to dump the keys during the traffic capture. Otherwise, it is not possible to generate a suitable keylog file to decrypt captured traffic. You can use the right-click menu or Edit, Preferences, Protocols, TLS menu to add. Remove keylog files. Adding keylog files with the right-click menu. Adding keylog files with the Edit, Preferences, Protocols, TLS menu. Viewing the traffic without the keylog file. The image shows that the traffic details are visible after using the key log file. Note that the packet details and buys pane provides the data in different formats for investigation. Decompressed header info and HTTP packet details are available after decrypting the traffic. Depending on the packet details, you can also have the following data formats: frame, decrypted TLS, decompressed header, reassembled TCP, reassembled SSL,